Hello, everyone. I see some messages popping in. I assume you can see me, but there's no feedback for myself. Can you hear me okay? Oh, great. Thanks, Gurpreet. Welcome to this session on integration. We have 3 exciting papers. Oh, Nicola says the sound's a bit low. Let me see. Maybe I'll just speak louder. Is this better, Nicola? Can you hear me better now? Okay, thanks. Yeah, welcome to the integration session today. 3 exciting papers. We'll start off with the first, which sounds like a dream, zero-variance transmittance estimation by Eugene Dion and Jan Novak. This is a pre-recorded session, and I am looking. So is there somewhere I need to click for this?
Hello, my name is Jan Novak, and I will talk about zero-variance transmittance estimators that we worked on with Eugene Dion. Transmittance of light through material is a fundamental quantity that we need to estimate to render images with translucent objects, such as these. However, you will not find any such images in our paper. The paper presents a theory for deriving zero-variance transmittance estimators. And it so happens that the practical realization of the theoretical estimator has already been published in the past. So do not expect any new practical algorithms when reading our paper. Rather expect a new derivation, perhaps a new insight into the problem of transmittance estimation. Here we see a reference image showing the transmittance through a cumulus cloud rendered with many samples per pixel. If you were to take just one sample per pixel, you would observe noise. And this is true for all unbiased transmittance estimators. They exhibit variance. Our goal is to see if we can take one of these estimators and fix it to have no variance at all. Most of the existing unbiased estimators can be categorized as either null collision or power series algorithms. There are numerous correspondences between these two classes, so if we manage to fix or at least improve one class, chances are good that the fix could extend to the other class. For the rest of the talk, we will only discuss the ratio tracking estimator and the derivation of its zero-variance version, but the paper also includes a similar derivation for the next flight estimator. Let's start by reviewing the idea of null collision algorithms. In addition to the real medium in the scene, these algorithms utilize also a so-called null medium. In the real medium, photons collide with the material and scatter around and get absorbed. These collisions are difficult to simulate in an unbiased way if the real medium is inhomogeneous. That's where the null medium comes in. In the null medium, photons also collide with the material, but they do not change the direction of flight and they don't lose any energy during collisions. As such, the net effect of this medium on light transport is null. And since the effect is null, we are free to add as much of the null medium in the scene as we like. For instance, we can add just the right amount such that the combination of the real and the null medium is homogeneous. Sampling collisions in such a homogeneous medium is trivial. The only caveat is that some collisions are real and some are so-called null collisions. The random walks that this procedure yields are statistically identical to those that photons take in just the real medium. This is the main idea behind null collision algorithms. Let's now talk about estimating transmittance using the ratio tracking estimator. Consider the segment between the points A and B here. Our goal is to estimate transmittance along the segment, that is, the fraction of light that will travel all the way from A to B. More formally, transmittance is defined as the probability that a photon will not interact with the medium along the segment. This probability depends on the density of the medium, more precisely on the optical thickness of the medium, which is computed by integrating the extinction coefficient along the segment. You can think of the extinction as the density of the medium. The higher the extinction along the ray, the lower the transmittance. As mentioned before, in null collision algorithms, we first add the null medium to make collision sampling easy. The null extinction μn is typically defined as the difference between some upper bound and the real extinction. The bound is commonly referred to as the majorand. The transmittance is defined as the probability that a photon will fly along the segment without interacting with the real medium. Ratio tracking estimates this probability in the following way. It samples the distance to the first collision in the combined medium. The sampling PDF is the product of the majorand coefficient and the transmittance through the combined medium. At the sampled collision point, we compute the probability that this collision involves the null medium. This probability equals to the ratio of the null extinction to the majorand. The algorithm records this ratio and repeats. It samples the next collision, records the ratio, and repeats again until the sampled collision exceeds point B. The product of individual ratios becomes an estimate of the probability of flying along the segment without hitting a real particle. And that's how ratio tracking estimates transmittance. Due to the random sampling, the locations at which we evaluate the null extinction will vary between realizations of the estimator, and the product of ratios will therefore suffer from noise. The million-dollar question is, can we get rid of this noise? It may appear that the only degree of freedom that we have is specifying the amount of the null particles. Everything else seems to derive from there, the distribution of collisions, the ratios. But that's actually not true. We can detach the sampling of distances from the media. The reason why this is not so obvious is because the estimator has been derived using intuitive arguments where some terms implicitly cancelled out. If we keep these terms, we will immediately see that we have a free choice in designing the distance sampling PDF. And we will exploit this free choice to derive a PDF that leads to a zero-variance ratio tracker. We need to formalize ratio tracking first. One way to do so is to start from the Volterra formulation of transmittance, which was introduced by Ilyan Georgiev and colleagues. The Volterra formulation is recursive. Georgiev and colleagues also showed how to inject the concept of null particles. When this is done, these new transmittance terms appear. This equation can be turned into a Monte Carlo estimator, which samples distances. And if the sampled distance exceeds point B, the estimator evaluates this fraction. Otherwise, it evaluates this other fraction and recurses to estimate transmittance along the remainder of the segment. It is easy to see that the estimator becomes the aforementioned ratio tracker that samples collisions in the combined medium. In that case, the terms neatly cancel out, leaving us with the familiar ratio of null extinction to the majorand. But the estimator is general, and it permits using an arbitrary distance distribution. The question is, what distribution would remove all variance from this Monte Carlo estimator? An estimator with no variance returns always the same value, independent of the chosen random numbers. And to be unbiased, that value must be the true transmittance. This observation will serve as a constraint that we will impose on the estimator. Let's consider the second branch. We demand that it equals to the true transmittance. This is satisfied with the following distance sampling distribution. Note that this is the distribution of only the null collisions along the segment, meaning in order to yield zero variance, the estimator must sample collisions only within the null medium. Let's recall the standard ratio tracker. It samples collisions with the combined medium and evaluates the simple ratios. The zero-variance ratio tracker shall sample collisions only with the null medium. It is somewhat remarkable that to estimate transmittance through the real medium, we should sample collisions only with the null medium. Okay, we could do that, but where's the catch in practice? The catch becomes apparent when trying to evaluate the estimator as the fractions reduce to the actual transmittance functions which we are trying to estimate in the first place, so that's not good. And no matter whether you cancel the terms out or keep them there's always something intractable. That shouldn't really surprise us. zero-variance estimators are not practical. Their value is in showing us the ideal that we should try to approach using practical methods. Let's do that. Let's use an approximation of the null extinction which is easy to sample and its transmittance is tractable. When sampling collisions in this approximate null medium, the estimator becomes tractable. It will have some variance, but if the approximation is close to the null medium, the variance should be low. The last important question to ask is whether this approximately zero-variance estimator is novel. It turns out that it is not. It has been around since 2014 under the name residual ratio tracking, which I happened to work on with Andrew Selly and Wojtek Jarosz. Why did we not see this similarity right away when Eugene approached me with the idea of applying zero-variance to tracking algorithms? The residual ratio tracker has been developed using very different arguments. The goal was the same, to reduce variance, but the steps to get there were very different. You can see it when you compare the terminology. This hatched region is in RRT called the majorant of the residual extinction, which is pretty cryptic. Approximate null extinction is easier to understand, I think. Also, the zero-variance approach needs no concepts of control and residual extinctions. So the nomenclature in this paper is nicer, and the postulation of the estimator better grounded using the zero-variance theory. Given that the practical algorithm is known already, there is not much point in repeating the empirical analysis. Here is just one example from the 2014 paper. The improvements depend on how well the approximate null medium follows the actual null medium. In this particular scene, the improvements are easy to spot. I'd like to conclude by saying what we did, but also what we didn't do in the paper. We presented an application of zero-variance theory to transmittance estimation. We derived the ideal last event and collision estimators, namely zero-variance ratio tracking and zero-variance next flight ratio tracking. And we pointed out that a tractable realization of one of the zero-variance estimators amounts to the existing residual ratio tracker. Since we did not invent a new practical method, we also did not include any new results in the paper. This was a deliberate decision as we did not want to create the impression that we present a new method. That being said, we hope that the derivation will stimulate your thoughts and will inspire developments of new transmittance estimators in the future. Thank you.
Hello, everyone. Thanks, Jan, for that. Can you hear me better now?
Yes. I can hear you.
Okay, sorry, everyone. It was a mic setting. Thanks for your talk. Does anybody have any questions first? No question? Okay, there's a lot of cooing. Okay, good. So Jan, I didn't catch that subtlety at the end where you compared your, to your old variance tracking paper. Could you just say a few words about that again? Especially, this hatched region that you called something else. Could you just say why? I actually didn't see why they're similar.
Yeah. It really amounts to exactly the same algorithm. If you were to code it up, you would end up with the same code. It's just the theory that you use to arrive at that algorithm is very different than the arguments that we used in the original paper. So in the original paper, or I don't want to say original, the residual ratio tracking paper, the 2014 paper. In that one, the idea was we have this medium, we need to integrate the extinction function somehow. Perhaps we could come up with an approximation and integrate that part analytically, and then we would be left with this residual component, and we would just track in the residual component. So there is this concept of control medium, which is piecewise something that you can integrate, and then there is the residual component in which you would perform ratio tracking. So hence the name residual ratio tracking. with Eugene, what we tried to do is to derive a zero-variance algorithm, right? And we ended up with an approximation, because zero-variance theory never gives you something practical. You actually have to cut the corners at some point. And this approximation turns out to be exactly this residual ratio tracking algorithm.
Ah, I see. Okay.
Okay, so there is you can actually see that, for instance, the transmittance through this control medium, this approximation, it also appears there with the zero-variance approach. It's somewhere in the Monte Carlo estimator. When the terms cancel out, you would actually see, for instance, this control transmittance, this transmittance through the control medium. So it's we didn't anticipate this at the beginning. It was sort of an curious or interesting finding throughout the process, where we tried to relate it to this older tracker, and we realized actually that yes, it's identical. It's the same thing in the end.
Okay,
so
thanks.
Yeah.
There are a couple of questions here. First from Wojtek Jaros. Jan, thanks, Jan, for the talk. Very interesting. I guess you allude that this is future work, but do you have a sense of how the new way of thinking about RRT as zero variance might help find new estimators?
Yeah, that's a great question, actually. And that's what we are hoping that, yeah.
And he continues, for instance, would you choose the control or approximate null medium differently now?
The zero variance theory is a little bit more direct. I think that's Eugene can comment on this, but I think that's the thing that we appreciate. It goes directly to what is the ideal. It tells you what the ideal is, and then you just know you can never reach the ideal, so you approximate this thing that you should ideally do. And that's the advantage over this control and residual argumentation, where you sort of say, oh, what could I do easily? Maybe this control medium, I will design it such that I can do it easily, and then we have this residual medium, and so on. So I think that the benefit of the zero variance theory is that it points directly to what is the ideal, and then you can start thinking, how should I approximate the ideal? And so maybe that could be an interesting insight for transmittance estimators that don't go directly to this ideal, but try to get there through some different arguments. I don't know, Wojtek, if that answers your question.
Okay, so Wojtek's here. We need to wrap up very soon, but since Wojtek only just got here, do you want to add something to that or to your question?
Yeah, so can you guys hear me okay?
Yeah.
Yep.
Yeah, so in the residual ratio tracking, we also know the ideal, which is make the control exactly equal to the heterogeneous extinction, and you get zero variance. So I'm curious if looking at it as a zero variance estimator would tell you how you should approximate that differently, right? So like if you think of it as a majorant, or sorry, as a control, like does that give you some different way of approximating it than as a approximate null? Is that the right way to think about it, or is there some other way that you would try to approximate things to give you lower variance if you look at it one way versus the other?
Well, in the end, it's the same approximation. If you think about it either as a control medium, which is trying to approximate the real extinction, or if you think about it as an approximating the null medium, in both cases, it's the same function, it's the same approximation. You are just, the difference is whether your reference point is 0 or your reference point is the majorand, right? And you are talking about this difference or that difference. But in both cases, you are trying to match the actual extinction as closely as possible.
Okay. In the interest of time, I'll chat with you guys in a room or something later.
Right.
Thanks.
Okay. All right. Thanks, everyone. We need to move on to the next paper now. Okay. Thanks for the talk, Jan, and thanks for questions
Gladly.
as well. Yeah. Well, yeah, so sorry, I was having some trouble with my mic when I joined first. My name is Karthik Subar, and I'm chairing this session, and it so happens that the next paper is mine. So I'll just let you listen to the pre-recorded video, and then take questions after. Oh, this applause is overwhelming, but I'm guessing Pascal. Hello, everyone, and welcome to this talk. We'll be dealing with particularly two different problems that appear consistently intertwined in computer graphics. One of function reconstruction or regression, as you can see on the left, and the other being numerical integration or estimating the area under a curve, as you can see on the right in this picture. There have been several approaches to this in computer graphics literature with different types of bases, and they are used to sort of produce interpolates for functions given point evaluations. But these methods or these bases are also useful when we need to perform numerical integration. And of course, the natural question then is, why can I not just use a neural network as my interpolant? And of course, the answer is you can use it as an interpolant, but if you would like to know the integral of that function that the neural network represents, then it turns out it is not so trivial. There have been several methods that do this for specific neural networks, and I will leave the related work section out in this talk, but please refer to the paper for details. This brings us to the central sort of topic of this talk, which is a QNet, or a network that can be used for low-dimensional integration of neural proxies. Hi, I'm Karthik Subar from the University of Edinburgh. This talk is going to be fairly general. I would refer you to the paper as well as the accompanying video for a more detailed treatment of this subject. What I'll do is I'll start off with how can you actually use QNets, and then take you through the various steps to give you a better idea of how where it's useful. So how do I use a QNet? Typically, we're all quite comfortable with training a neural network given point samples of a function. On the left here, we can see a function over a two-dimensional domain evaluated at several points shown with triangles, and the value of the function at these points is shown using circles. And given these values, we can train a neural network that approximates the function and therefore can be used to evaluate this function at new points in the domain. However, what the topic of this talk is given that network, how do we estimate the area under the curve as shown on the bottom figure, where the blue area, the blue volume, represents our target. What I'll show in this paper is that we can take the weights of that neural network that has been trained, pipe that into what I'm going to call a QNet, and out comes the volume, or the blue shaded region, which is the integral of the function over two dimensions. QNets are fixed weight networks that are parameterized by the dimensionality of integration. So for example, here we have a function over a 2D domain as shown above, trained first so that we produce learnable weights W. Then these weights are input to a 2D QNet to produce the double integral of f, while they're input to a 1D QNet to integrate one of the dimensions of f, as in this case, y. For details, please refer to the paper on how different subspaces may be integrated. Another advantage of QNets is that the subdomain, or the domain of integration, can be changed. For example, here we show two different integrals, both double integrals, but one over the domain D1 and the other over the domain D2. The procedure for calculating these two integrals is identical, but the weights in the QNet are adjusted appropriately in this case of D2. A third advantage of integration via QNets is that they accommodate input transformations, affine transformations, to the input space seamlessly. For example, here, if instead of inputting x to the network to get f of x, if we inputted a transformed version, imagine a rotated image instead of an image, then the output would be f of t of x. And we show in the paper how integrals of transformed functions can be obtained without having to retrain the original network. Thus, in summary, all of these different operations can be performed without having to retrain the original network, which is one of the major advantages of using a QNet. The key insight behind QNets is easy to see. So for example, here we have a network with one hidden layer and one output layer. The hidden layer has an activation function that is a logistic function, and on the output layer we just have a linear activation. It has a one-dimensional input and 3 neurons. And we can see that in this case, we can write the output function f as simply the sum of 3 scaled sigmoids. Naturally, if we can write f as the sum of three sigmoids, then we can write its integral as the sum of the integral of three sigmoids. And it turns out in 1D, the integral is a soft plus, and this is fairly simple to do analytically. However, in high dimensions, we show that this can be written using polylogarithmic functions. We validated our estimator using QNets via different analytically chosen integrands first. Here we show the three classes that we used. First, we used smooth functions, which are just a mixture of Gaussians. Then we used a truncated mixture of Gaussians. You can see that the green region is the zeroed out space. And finally, we used hyperrectangles or collections of rectangles to represent a binary function, just to test the effectiveness on highly discontinuous integrands. We generated multi-dimensional versions of these up to dimension 12 and gathered statistics on how QNets performed when we tried to integrate them. Please refer to the paper for details. Here I show just a snapshot of what the marginals look like. So on the left you see a three-dimensional mixture of Gaussians. In the middle you see a set of plots which are 2D marginals obtained by integrating one of the dimensions, and you can see three of them across the columns because each one results from marginalizing a different variable. On top you see our closed form solution, and at the bottom you see the reference. As can be seen here, the closed form solution matches the reference quite closely. On the right, we see 1D marginals resulting from a two-dimensional integration of the function in 3D. Again, we see that QNets produce quite a high fidelity approximation for the marginals. Another example here that I'd like to highlight is that when used as a control variant, the QNets can be quite useful. For example, here we show two plots. On the left, we show relative error, and on the right, we show relative variance. On the x-axis, we see nu, which is a parameter that expresses what fraction of samples were used in the Monte Carlo estimator. So to the very end on the right, we would expect to see 1, where all samples were used to integrate via Monte Carlo. At 0, we use 0 samples for Monte Carlo integration. Instead, we use all of the samples to construct the proxy, which is then integrated via a QNet. So if you look at this curve, the curve goes smoothly from just using QNets on the far left to using QMC or MC purely on the far right. Of course, we don't show the plot all the way to 1. But we show, using dashed lines, the errors and variances obtained using QNet as well as MC and QMC. The red curve shows the behavior of QNets when used as control variates with different fractions for producing the proxy versus Monte Carlo estimation. Although the error doesn't reduce significantly, we can see that the variance does indeed, for a large set of fractional weights, go below Monte Carlo and QMC variance. One of the applications that I would like to highlight is that of inverse rendering. Here is an example of a bull placed inside a Cornell box scene with two parameters of interest. 1, the rotational angle of the bull about the vertical axis, and 2, the roughness of the material on the bull's surface. Our goal is to observe a small patch of pixels on the right wall, the green wall, and to predict θ1 and θ2. Of course, we can do this with standard inverse renderers that are available, such as Mitsuba 2, and we obtain point estimates across iterations. Just plotting these iterations, we see that for θ2, depending on the size of the patch observed, we get different estimates. So the first plot on the right shows these evolving across iterations compared to the reference value, which is shown as a horizontal dashed red line. What we also did was gathered all these point estimates and produced a histogram, or several histograms, one for each window size. And we can see that for some window sizes, the histogram, the mode of the histogram points to the true reference value. Of course, this is all with point estimates, and what we wanted to do was to take a Bayesian approach to this, where we would get a distribution over each of these parameters that would point to what the reference values were. Using our method, we can see the plots on the right for both θ1 and θ2 evolving from light gray to dark, almost black. And we can see that over several iterations, the distributions evolved to predict what the ground truth values are, which are shown as vertical dashed red lines. What we can see from this is that in addition to just predicting what theta... Okay, it looks like maybe because the video was longer than 12 minutes, it has been truncated. Well, I guess I have many questions for myself, but thanks to Gurpreet for setting this off. Gurpreet, do you want to ask your question? I can see the text, but happy to listen to your voice.
Can you hear me?
Yes.
Yeah. Thanks for the nice talk. Yeah, sorry, it got cut. We are struggling today a bit, but
that's fine.
Yeah. So yeah, I was just wondering. Okay. Yeah, really good talk. Yeah, okay. I like the way you presented it. So yeah, as my question says, like in classical integration, the approximation error comes from sampling itself, and I was trying to wrap my head around like what exactly are these pointers which will affect the quality in QNet, even for 1D and 2D cases.
Well, yeah. So the formula itself is analytically is accurate, which means has zero error for the function represented by the neural network. So the question of error comes down to how far away from the true function is your neural net approximation.
I see.
So if you've invested, millions of neurons, or if your function is approximated perfectly, then the error is zero. So all the error stems from how far away the function is in its approximation. I see.
But isn't it making it the whole problem more of a reconstruction problem than integration?
Well, so you could say that, but the way I view it is different. The way I view it is we know how to do reconstruction fairly well.
I see.
And if we can do reconstruction well, can I use that same methodology to also integrate? So for example, if I can construct a neural network that we know works well to approximate functions, how do I then reuse what I've trained to obtain its integral?
I see. Thanks.
Yeah, so Ravi has a question on how does this compare to AutoInt? So in the paper, we do specify what the differences are. Of course, the goal of AutoInt is similar, but the main difference here is in the marginals and the computation of the marginals. Sorry, I should have said the methodology is very different, but the goal is similar. One of the things that AutoInt can allow you to do is to have multiple layers. On the other hand, one key advantage of QNets is that you can marginalize any set of variables. In AutoInt, your marginalization is limited to the sequence of variables which were used while constructing your integrator. Whereas in this case, you can choose arbitrarily any sequence of variables and marginalize. So there are pros and cons to both, and I've tried to highlight them in the paper. Happy to take questions beyond that if you have any. Okay, Ravi, do you want to join by video, or are you happy with that answer? Okay, no answer. So
maybe I can join in help here. Seems like people are not really up to that at this point. So I'll follow up with my question. So there is this reconstruction issue which you were just explaining, but like in higher, like there was this in your plots which you were showing, there was this point where the error or the variance was going higher. So if it is analytic, I mean, I would expect zero variance first of all, right? And of course, it depends on how well it approximates the true integrand. But like, why the error starts going up? I mean, was it with respect to some variable? Which
do you mean in the plots I showed in the presentation, or in the paper?
Yes.
So that one, you mean the one with the control variance?
It was with the control variant. I didn't see that. Okay.
Yeah. So that was a control variant thing. So
okay.
as you know, you reduce the number of the control variant. You're trading off between how many samples you invest to construct the proxy versus how many you're going to use for MC. So obviously, if you use fewer samples to construct your proxy, then it becomes a larger source of the error.
Right. I see.
Right. And if you invest all your samples into constructing the proxy, then of course the error from your proxy is the error. Right. So that was the trade-off that I was showing there.
I see. Okay.
But more generally, of course, you know, for certain integrands, you know, 100 samples just as a number with 1 million neurons is not sufficient. Whereas for others, you know, it's more than sufficient. So there's a lot of work, I think, to be done on analyzing the fidelity of neural reconstructions themselves. But the goal of this paper was more to say, if you can reconstruct a function, can you also integrate it without any special training?
Right.
So maybe that's another difference with the philosophy of auto-int, as Ravi asked.
Right. There is another question from Wojtek. He's saying, how does this
Yes.
neural control variant work?
Yeah, so that's another paper that we have discussed in this. So the neural control variance paper is slightly different in that what they try to do is to warp functions while preserving their integrals. So if I start with a distribution and warp it to match the target function while preserving its integral, then I have an idea of what the integral is at the end. So it's fundamentally different in its approach. And then once I have that, because I know the integral, I can use it as a control variant.
I see.
Jan has a question as well.
Yeah, I would like to have a follow-up on this. So when I saw your paper, I felt like you solved this problem that we had to sidestep with the neural control variance paper, where we had to use the normalizing flow and sort of reformulate so that we can get the integral, and you can provide the integral. Now, my practically minded question is, how far do you think you can push this approach, your approach, in the future in terms of the number of layers in the network?
So that's the obvious shortcoming in this paper, because it started off as a pet project of mine, and then so it is tricky if you have multiple layers. So we need to introduce something between layers in order to extend it. I'm working on that, but I don't have an answer yet. So there are challenges in that. But the thing I'd like to reiterate is that even with one layer, you can actually go quite far. And one thing that I am excited about this is that these QNets are fixed, which means you can actually lay them out in hardware, one for each dimension. And once you've trained your network, you can think about just sending the weights to these hardware pipelines of QNets to get integrals. That I think is very exciting. So even though your function itself can only be represented using a one-layer network, I think these sorts of advantages might be interesting in the future.
Yeah, this is amazing work. Thank you very much.
Cool. Thanks, Jack.
So maybe Karthik, we can move ahead.
Yes.
Yeah. So let's give big thanks to Karthik for his talk.
Yeah.
Yeah, and Arnold just.
Yeah. Okay. Thanks for those questions. The final talk in this session is going to be live, I believe. The title of the talk is Stochastic Generation of TS Sample Sequences. It's a paper by Andrew Helmer, Per Christensen, and Andrew Kensler. We have Andrew Helmer here to deliver the talk. Thanks very much.
Yeah. Thanks, Karthik. Yeah, I'm Andrew Helmer, and I'm really excited to be here presenting the work that Per Christensen and Andrew Kensler and I have been doing. So to give a little background on this paper, Per and Andrew and Charlie Kilpatrick published their PMJ paper a few years ago and presented at EGSR. And shortly afterwards, Matt Farr came up with a really clever optimization to generate the PMJ02 and PMJ02B endpoints from that paper more efficiently. So we started talking about how to extend this from 2 dimensions into higher dimensions. And we realized that there was a deeper connection between the PMJ02 generation and randomized quasi-Monte Carlo sequences. So that's sort of what this paper is about. So for all these papers, what we want to do is to generate S-dimensional points in the unit hypercube that we're using to evaluate rendering integrams in path tracers specifically. And there are really 3 important characteristics for sample points in path tracers. they should be stratified, and they really also need to be actually progressively stratified sample sequences like the solvable 0-2 sequence. And that's actually not quite enough. They also need to be at least somewhat randomized. In fact, the three of us are such believers in the importance of this randomization that we asked my partner to flip a coin to decide who would be the second author of this paper. Anyway, the PMJ paper goes into more detail on why these are important characteristics. I think it's also worth noting that it seems like most, if not all, production path tracers are using progressively stratified sample sequences that are in some way at least a little randomized. So there are really two typical approaches to generate points with these properties. The first is using stratified sampling, and that's the PMJ approach, where we would have data structures that keep track of the strata and what points are in them. And those data structures might be something hierarchical, like a KDA tree, or they might be just flat arrays. And then when we want to generate new points, we need to check or traverse those data structures. The other approach is using randomized quasi-Monte Carlo sequences. And quasi-Monte Carlo sequences have a mathematical construction that gives a deterministic set of points in the unit hypercube that are rigorously stratified. And then we need to randomize those points in a way that maintains that stratification. The most notable of these is Owen scrambling, which, if you're not familiar, we discuss in the paper. So our approach is sort of bridging the gap between these methods, as I alluded to earlier, or maybe you could call it kind of a hybrid, where we're going to use mathematical rules that we're borrowing from quasi-Monte Carlo to determine the strata to place new points, but those points are still going to be placed randomly within the strata. And with our approach, we can generate PMJ02BN points. We can generate various unscrambled quasi-Monte Carlo sequences. As we'll get to later, we've started a little work on optimizing these sequences, and I think this makes it a lot easier. But even if you just want to generate PMJ02 points, using this approach is a lot faster, and it's also a lot easier to implement. And because we can borrow rules from quasi-Monte Carlo, it's really easy to extend it to higher bases and higher dimensions. Compared to Owen scrambled quasi-Monte Carlo sequences, it's also faster and easier to implement. And as I mentioned, we can do this optimization with best candidate sampling or gradient descent. We also talk about in the paper how we can extend pre-computed sequences or generate coordinates arbitrarily without using any memory or keeping track of the stratifications. So to give an idea of how this works, I'm going to walk through the generation of the first 4 points of an Owen scrambled solvable 0-2 sequence. And I think this is pretty intuitive. So the first point we'll place randomly in the unit square. And then conceptually, both the x and y dimensions will divide their unit interval to 2 subintervals. The second point is going to be placed in the adjacent subinterval of the first point on both dimensions. Then we divide the unit intervals again. And the third point is going to be placed adjacent to the first point on the x dimension, but on the y dimension, it's going to be placed adjacent to the second point. So we're using different points on different dimensions. And the fourth point flips that. It uses the second point on the x dimension and the first point on the y dimension. And with this permutation, we've guaranteed that whatever random numbers, however we randomly place these points, they're going to be stratified in all base 2 elementary intervals. In the case of these 4 points, they're multi-jitter. So the question is, how can we extend this to more points? And the observation that we made first with PMJ02 sequences was that we could do this permutation with just a single carryless addition in base 2, which is also a bitwise exclusive OR. And then when extending to the next 4 points, it was still just another XOR. And in general, when doubling the length of the sequence, we only need to know one value to XOR by for each dimension. And it turns out those values are actually really easy to compute from the generator matrices of a quasi-Monte Carlo sequence. So using that, we can get something like this C++ implementation of fully Owen scrambled solvable 0-2 sequences. And it's very short. You can look at it pretty quickly and see it's O of 1 time per sample. It's really fast since most of what it's doing is just one random coordinate per dimension. I mean, one random number per coordinate. And the samples are still being placed stochastically within their strata. It's also very easy to extend this to higher dimensional sequences. We just need more XOR values. The supplemental code, we have 64 dimensions worth. And the paper then goes into how we can generalize this to other prime bases, and it's still pretty straightforward and fast. And in particular, I want to emphasize that we can use this to generate 0S sequences. So Henri IV gave a construction of 0 sequences in prime bases using Pascal matrices. And with that, we can generate things like a base 303 sequence, which is 3-dimensional. This is just showing 2 dimensions. But to give an idea of how well stratified this is, for the first 27 points, they're jittered in 3 dimensions. Also, all 3 2D projections are well stratified, and all of the 1D projections are well stratified as well. And this is a really useful property for rendering integrals. So for something like this, a classic 5-dimensional rendering integral with multiple point sampling and multiple lights, using a 0.5 sequence actually does achieve the lowest error of any available sequences. As I mentioned earlier, the characteristics of this generation make it more optimizable. So we can, of course, do this candidate sampling. Probably more interestingly, we did an experiment using gradient descent to optimize progressive minimum distances of soluble 0.2 sequences. And it very quickly finds the global minima at some low sample counts. It's quite unstable at high sample counts. If people are interested, I can go into more detail on that. So we started using simulated annealing, which basically just randomly flipping the bits of the random numbers. It doesn't use the gradients at all, but it does take advantage of how much faster this is. And we've also started using Achman and Wonka's really beautiful formulation of blue noise from their recent paper, optimizing dyadic nets. And that allows us to optimize, say, soluble 0.2 sequences for blue noise at whatever sample counts we want. So in this case, they're optimized at 1,024 samples specifically. And they have some regularity, but they do have good spacing overall. This is 6 consecutive runs of this optimization. And the average Fourier spectra, we see that it does have that nice low energy disk that we would hope to see with blue noise. We can also optimize these sequences across multiple sample counts, in particular because their formulation of blue noise is well normalized. So we can do powers of 2. It does improve the spectra and spacing considerably over, say, best candidate sampling, but powers of 4 really worked quite well. And I want to emphasize, these are still just soluble 0.2 sequences. So if you wanted to do something like optimize a 2-dimensional sequence, you could then add more dimensions using whatever technique you like maybe you're using Blaine-Cross and Burley's hashing. I think all of this is just sort of laying the groundwork, and there's a lot more that can be done with it. So in particular, I think all the optimization stuff that we've done has been pretty early work very recently. So I think that could be improved quite a lot. We don't go into a lot of detail on error comparisons. And part of the reason for that is that we actually did quite a lot of render comparisons, and there's not really a clear winner. All of these are pretty good sequences. So I think there could be, I think it would be more interesting to look into which of these sequences are more well suited to particular renders, rendering integrals, and assigning dimensions, and so on and so forth. And finally, I think we could design new generator matrices for rendering. I think a particularly interesting one would be something like 202 sequences that combine into a 4-dimensional jittered sequence. And this can be done with generator matrices. And that actually might, I think, work better than a 4-dimensional soluble sequence. So to take a step back from all of this, this is all really just a different perspective on Owen scrambling, maybe a sort of partially continuous perspective. And I think the benefit of it is that when taking that perspective, some problems become easier. So the original problem that we wanted to solve, how can we extend PMJ02B endpoints to higher dimensions, seemed initially pretty tricky. But once we realized this connection, it really became quite a lot easier. Yeah, and that's it. Thank you so much for listening to the talk, and take any questions.
Oh, thanks, Andrew, for the wonderful presentation and sticking to time. Yeah. Well, I guess there are no questions yet, but so I can start off with a couple of questions that I had. First of all, I mean, what do you think is the biggest sort of problem that needs to be tackled for randomized QMC? And maybe related, I'll just staple the second, for does the introduction of randomization create any extra benefits for higher dimensions? Hello, Per, hi there. Yeah.
Yeah, so the randomization, I mean, in the PMJ paper, they talk about how unscrambling actually does improve integration performance because it's decorrelating lower digits of the sequence. And we did notice that. So actually, it's hard to compare them exactly, but on the whole, unscrambled solvable sequences that were high dimensional performed better than say PBRT's solvable sampler, which isn't scrambled. And there's also other characteristics, like it makes it, I think, easier to do variance analysis for adaptive sampling. But I think, as I mentioned, I think probably the more interesting direction is allowing for better optimization. I mean, that's really, I think, the sort of future benefit of this.
Right. So that's of your paper specifically, but I'm just wondering more generally the benefit of randomization in randomized QMCs.
Yeah, so yeah, it actually does improve integration performance. There's a Art Owens there's a theoretical asymptotic convergence on smooth integrals, like say Gaussian, and randomization actually achieves better convergence.
Right.
Does that answer your question? Sorry.
Yeah, it answers the second one. The first one was what the biggest problem is in randomized QMC, you think?
Oh, the biggest problem. Yeah, I think that's a good question. Maybe, I don't know, maybe that it's been hard to optimize in the past.
Okay.
Yeah.
Right, so, sorry, Gurpreet has a question.
Yeah, just a quick question. I was just wondering, like, if you try to understand how the convergence of these sequences behave. Like, I didn't see any convergence plots, so.
Yeah, So for the most part, these sequences have pretty well studied theoretical convergence, so I kind of stuck away from them. But I forgot the exact. I don't remember the exact convergence on smooth integrals. It is related to the dimensionality of the problem and the dimensionality of the integral. And these sequences, they're all TS sequences, so they all have the same asymptotic convergence. Right. And they're all kind of just about optimal for non-periodic functions. And then for stratified sequences, I think it depends, Per probably remembers better than I do, on the sort of effective dimensionality of the discontinuity.
I see. And just like last follow-up, so you mentioned this Gaussian function which you're trying to optimize. So this was, I didn't really follow, like it was to replace the unscrambling part completely?
Yeah, so actually our method is equivalent to unscrambling. So it's this stochastic generation generates sequences that are exactly identical to unscrambled sequences. And it's just a different way of doing it.
I see. Okay, thanks a lot. Very nice.
Wojtek has a question. Are all 2D projections for any pair of dimensions chosen stratified?
Yeah, for the 0S sequences, that's correct. So for a 0-3 sequence, the 3 2D projections are all going to be well stratified.
That's very cool. Per, do you have anything to add?
No, I'm mostly here for moral support.
Okay, great. Okay.
I mean, thank you. So I just wanted to reiterate. So, I mean, so the benefits here compared to our paper from EGSR 3 years ago is that, first of all, the sample generation is way faster and the code is much simpler. You know, it's only what 20 lines of code or 30 lines of code. And then the fact that it generalizes to higher dimensions is exciting as well. And then in addition to all of that, Andrew has been working the last couple months, I guess, on these optimization aspects, how to optimize the actual placement of the sample points using, you know, so he showed that plot with the blue noise properties, which are quite impressive. Yeah, so there's a paper by Ahmed and Wonka at the upcoming SIGGRAPH where they do blue noise optimization of sample sets. And so the stuff, the work that Andrew has been doing lately is the equivalent, but for sample sequences.
Okay, excellent. Congratulations. I mean, that code looks like it's going to have high impact. So it looks really cool that it's also condensed and compact. Okay, any other questions before we let Andrew go? Okay, that's it for this session. Thanks very much for attending.
Thank you.
Looking forward to the next session. Bye.
Hello, everyone. I hope you can hear me well. I'm Katharina Grösel, and it's my pleasure to chair this session on perception today. We have 3 very interesting presentations in this session, so please don't hesitate to ask your questions via video after each talk. We will start with the first presentation called A Low-Dimensional Perceptual Space for Intuitive BRDF Editing. The authors are Wei-Qi Shi, Seo Wang, Cyril Solar, and Holly Rushmeyer, and the presenter is Wei-Qi Shi.
Hello, everyone. Today, I'm glad to present our work, A Low-Dimension Perceptual Space for Intuitive Material Appearance Editing. The complex representations of the BRDF are not friendly to humans. The BRDF models, especially measured BRDF data, are often presented in high dimensions and they cannot be easily interpreted or understood without rendering. Our goal is to provide an intuitive representation for this data based on human perception and make sure the human visual system can perceive the difference between each data sample in this representation. To be more specific, given a group of materials, we can notice some are more similar to others. Some of the materials are glossier and shinier. It would make sense to rearrange these materials based on the perceived similarity, like this. The image on the top left corner is more shiny than the ones on the bottom right. This means that in our brain, we have already built a perceptual space for these materials. However, we can only tell the roughly relative relationships between material samples, and it will be difficult for us to quantify this perceptual space and provide accurate coordinates. For example, the materials on the top corner could represent metal-like materials. The middle ones could be plastic materials, and the bottom ones could be the rubber-like materials. If we make an abstraction of this perceptual space, it would look like this. According to the material perception theory proposed by Fleming, there are 2 steps when humans perceive and recognize materials, that is, classification and estimation. The classification is the step to recognize what kind of material it is, like the clustering process. And the estimation is the process to locate positions of each material sample within the cluster based on its properties. In this project, we focus on the estimation process for metal materials due to its diversity and unique properties, and provide an intuitive perceptual space that can capture the human perception for the material appearances. There are some previous works focusing on building perceptual space, using individual perceptual attributes, high-level descriptive words, or high-dimension features. As a comparison, we propose a solution to build a low-dimension perceptual space for measured material data. We learn perceptual embeddings from the crowdsourced data and build a continuous perceptual space by interpolating the measured data using the embeddings. Our work has 2 major contributions. The first contribution is low-dimension continuous perceptual space for tabulated metal materials that based on crowdsourced data that can be used for intuitive material editing. The second contribution is to prove that using the interface that combines image navigation and sliders could help users edit the appearance in perceptual space efficiently and accurately. Our proposed interface allows users to create BRDFs in tabulated form and avoid ambiguity of perceptual terminologies. To build the perceptual space, our method includes 3 steps. We perform a user study to collect crowdsourced data using Mechanical Turk. Then we show how to learn the perceptual embeddings using the NMDS model. At last, we introduce Gaussian process regression to interpolate perceptual embeddings and build perceptual space. For the data collection process, we gathered 39 measured metal materials from multiple datasets to cover a large range of material appearances. We used the 2 alternative force choice scheme on Amazon Turk to ask users to select which 2 of the images are more similar. We generate 6K unique triplets from the 39 stimuli using the adaptive sampling to maintain enough data samples without losing too much information. Each triplet is evaluated by at least 5 users on Amazon Turk. We use the training set to filter out unqualified users before they start the actual experiment. Each users need to finish 110 trials with 10 repetitive validation trials. Each validation set are repeated triplets used to check if they can provide consistent results. We end up with collecting data from 360 participants with 30,100 valid responses. Next, we use the non-matrix dimensional scaling to learn the perceptual embeddings from the user's responses. We convert the result of the triplet comparison as gram matrix K and optimize the rank of the matrix. We conduct an eigen decomposition on the optimization results to get all the perceptual embeddings stacked in matrix X. For more detailed math deduction, please refer to our paper. We introduce the hyperparameter lambda during the optimization to balance the matrix and the possible violation, represented by the slack variable epsilon. We measure the percentage of the violation between the prediction and the majority user responses and conduct cross-validation with the different lambda values. When lambda is small, the optimization focuses on reducing the number of violations, leading to smaller training errors. But the average dimension of the matrix K is 32, which means possible overfitting. When the lambda is large, the optimization focuses on reducing the rank of the matrix, leading to large training and validation errors. The prediction error reached the minimum point as lambda equals to 26, representing the model has the best generalization performance to deal with the violations. At this point, the first 4 dimensions of the embeddings have 99.2% of the variance compared with all dimensions, indicating that we can build a 4D perceptual space. Our final step is to build the perceptual space by mapping the embeddings to the measured BRDF data. To be more specific, given random coordinates in the perceptual space, we should be able to predict the corresponding measured BRDF with 4 million entries. We use the Gaussian process regression model to build the mapping because it provides a nonlinear mapping between the latent space and the BRDF data. And also it provides a uniform linear interpolation for the measured BRDF. And it guarantees continuous interpolation. Please to refer our paper for more details. Here we visualize each dimension of our perceptual space by fixing other dimensions. For axis 1, the major variation is the specularity. The highlight becomes sharper and the whole appearance tends to be glossier. For axis 2, we observe the changes in the grazing angles. The edge of the sphere changed from bright to dark as the increase of axis 2. Axis 3 captures the specular shape and the anisotropy. Notice the vertical part of the highlight starts from clear and regular dots and ends up as stretchy lines. The variation for axis 4 depicts the increase of the diffuse part while maintains the shape and the intensity of the specular part. Given the proposed perceptual space, our next step is to develop a new material editing interface prototype that can visualize each dimension of the perceptual space. Different from previous material editing interface, we do not want to represent each dimension with a single word that users may interpret in different ways. For perceptual dimensions, it is even more difficult to find ubiquitous and intuitive words to interpret them. Therefore, we want to use the appearance variation to define each perceptual dimension. By observing the image variation, users are expected to understand and interpret each perceptual dimension by themselves. We use the image grid to demonstrate each perceptual dimension and how it would influence the material appearance from a small value to a large one. Here is a video showing our interface, how our interface works. During the editing, users can either select the image in the grid or use the sliders. Either way, the image in the grid will update accordingly. The image grid will be centered at user's current selection, and the slider value will be updated. User can also change the step size of each dimension to view images with more or less variations. For evaluation, we want to test the effectiveness of the proposed perceptual space and the interface paradigm for material editing in the context of
Okay, it seems our talk ended a bit early. Maybe the author can continue what we missed.
Yeah, so basically the last part is about like the evaluation. Like, should I continue or should I just answer?
Maybe you can sum it up for us.
Oh, okay. So basically, we did some evaluation to test the accuracy and efficiency by comparing our interface with another interfaces, and we also evaluate like how users' behavior, like when they actually added the materials through the times. And also we conduct a survey to like examine how users are satisfied with their own result compared with the target materials. And also we discuss about the limitation and future works at the end of the presentation. Yeah.
Okay, thank you. So if there are any questions from the audience, please just send them in the text or ask them via video. I would like to know, with this work, what would it take to create a perceptual space for other material types? Because now you only focus on the metallic materials, right?
Right, yeah, that's actually a pretty good question. We actually discussed this as the limitation part in our paper. So yeah, basically our work only focus on the metal material for this now, but like to extend to other materials like plastic or cloth, it's very simple to actually like apply our like flexible methodology. By we need to like collect another we need to actually collect more user data by using another user study to actually show to ask them to do the like labeling to show how similarity they think between like all the stimulus. Yeah, so that's actually like a good start to extend our work to another material category. Yeah.
Okay, thank you. We have a question from Lorov Bosna. Thank you for a very nice presentation. Which kind of illumination is used for rendering?
So basically, we render all the stimuli using the same like illumination with the same like environment map, which is actually we adopted the same settings from another paper presented in SIGGRAPH 2019. We have that actually referenced in our paper, so you can actually find the details in our paper for that. I don't actually remember the exact name for the environment map we are using, but all the details are actually in our paper. Yeah.
Okay, thanks. There's another question from Nati Hoffman. The paper is a bit brief on extension to colored metals. Could you elaborate?
Yeah, so basically our current, like all the stimuli we're using is actually based on like in the grayscale, because we don't want our users to be like confused by the colors, because we are more focusing on like the material itself, not just the color. So yeah, we didn't actually mention too much about the color in the presentation, but like I said, the color can be easily added by in the LAB like lab space by adding the AB channels, and there are other like works already talk about how to do this. And also in our work, like we use the Gaussian Gaussian process regression model to do the interpolation. So once the color is added in the stimuli, the GPR model can easily handle the interpolation of colors. Yeah.
Okay, thank you. So what are your next steps? What are you working on right now to improve your method or to extend it?
Yeah, sure. So for the future works, like we are actually very interested in like introducing more material categories like the plastic and also like the cloth, so that we can actually see how those each small like island of the materials, like how we actually can study them in a different kind of ways. And also like it would be like interesting to incorporate like even SV BRDF in the future to see how the material works with the texture in like when human actually perceive those different materials. Yeah.
Okay, there's another question by Gurpreet Singh. There are recent methods and metrics developed using NN to understand and synthesize different materials. Where does your work stand compared to these works?
I'm not actually quite sure like which specific work like this audience actually referring to. So basically, if like this audience actually referred to the paper in the SIGGRAPH paper in last year about like using the machine learning to extract the high dimension features and then use that to be like perceptual space, the difference between their work and ours is that our space is very low dimension. It's only like 4D. But I remember in their work, they actually, the feature they extracted is like 100 or something like dimensions. So basically our work is very easy for editing. Like you see, like we actually kind of visualize all this kind of 4 axes so that user can easily tweak every dimension. And we can find, like we can try to interpret each dimension so that user can like build their own understanding about how this material space works, and then they can actually help them to edit the materials. But compared with the previous work with the high dimensions, I think it would be like relatively hard to actually edit the material in that high dimension space. So that's actually our like comparison. Like we didn't actually conduct exact comparison in our paper, in our work with their result, because it's kind of like not very like comparable like at this kind of stage.
Okay, thank you. If there are no more questions from the audience, let's thank our speaker.
Thank you.
And the next presentation is on modeling surround-aware contrast sensitivity. The authors are Shin-Young Yi, Daniel S. John, Anna Serrano, Se-Yoon Young, Hui-Young Kim, Diego Gutierrez, and Min H. Kim. The talk will be given live by Shin-Young Yi.
Hello, thank you for coming our presentation. My name is Shin-Young Yi. I'm presenting our paper entitled Modeling Surround-Aware Contrast Sensitivity. What is the contrast sensitivity function? You can see the spatial frequency of the sinusoidal pattern increases as you go to the right on the image, and the contrast decreases as you go to the top. Then our eye forms a borderline of visual perception of the sinusoidal pattern, like this concave curve. This curve roughly represents contrast sensitivity as a function of the spatial frequency. Let me introduce the definition of contrast and contrast sensitivity in more details. When we have an image with sinusoidally varying luminance along position, the contrast of this image is defined as delta L over L, where L is the average luminance and delta L is the difference between peak and average luminance values. When only the contrast is changed, while the average luminance L is fixed, the image and graph changes like this. When we're changing the contrast more and more, then we can recognize the sinusoidal pattern when the contrast is sufficiently large, but cannot recognize when the contrast is too small. So we call contrast threshold as the threshold value that determines whether the pattern is visible from an observer. The contrast sensitivity, denoted by S, is defined as the inverse of the contrast threshold. Intuitively, higher contrast sensitivity indicates the observer can resolve finer scales of luminance changes. Contrast sensitivity has been studied well over many decades. Among them, there are traditional studies on contrast sensitivity function, CSF, as Barron and Daly. But based on general display and printing technology at that time, they studied CSF on limited luminance ranges. There are several recent studies with wide luminance ranges, such as Mantiu and Werger, but they do not consider both stimulus and surrounding luminance as variables of CSF. In contrast, we will investigate a surround-aware CSF, which takes both stimulus and surrounding luminance into account. There is a surround-aware CSF study by Barton 2003. However, this work is based on limited viewing conditions measured in 1973. For instance, this experiment uses airplane dashboards under specific viewing condition, which is far different from display technology nowadays. So we made use of a state-of-the-art HDR display to measure contrast sensitivity with different surround luminance levels. This is our experimental setup, briefly. As shown in the left figure, each participant enter a dark room and sit in front of the HDR display with fixed viewing distance. After the dark luminance adaptation, the participant looks into stimuli as illustrated in the right figure, and they respond whether the sinusoidal pattern is visible or not. The entire stimuli has a 2-degree size sinusoidal pattern with different frequency luminance and surrounded by uniform intensity area with different level of surrounding luminance. Now we specify the variables of the experiment. Our surround-aware CSF is a function of 4 variables. First, the direction D takes a value horizontal or vertical, and the spatial frequency U determine how dense the sinusoidal pattern. The stimulus luminance L determines the average luminance on the sinusoidal pattern. Finally, the surrounding luminance Ls determines the luminance on the uniform intensity outside of the sinusoidal pattern. Our experimental data set will be available through our project website, and please refer our paper for more detail for experiment. From our experiments, we found that the CSF of horizontal and vertical directions does not have significant difference. Therefore, we omit the variables direction D by taking averages. Then we can consider our surround-aware CSF to have 3 variables, U, L, and Ls. For fixed stimulus luminance L, our measured CSF is shown in this plot. Each curve shows dependency of spatial frequency U, and each color of curves indicates each level of surround luminance Ls. When stimulus luminance L changes, the CSF varies as these 5 plots. However, finding an appropriate annihilating model to this trivariate function is so difficult. Therefore, our modeling starts from a slightly different direction. We introduced the relative sensitivity, denoted by R. The relative sensitivity is defined by the ratio of 2 values of CSF. The numerator is the CSF value at given variables U, L, and Ls, and the denominator is the CSF value when the surrounding luminance Ls is changed to the same value of the stimulus luminance L. Intuitively, the relative sensitivity indicates the amount that the surround luminance affects on the contrast sensitivity. Then we can plot the relative sensitivity from our measurement. When we plot the relative sensitivity as a function of the ratio of 2 luminance values, Ls and L, as seen in this plot, we found that the relative sensitivity R has a major dependency about the ratio Ls over L, and it has a minor dependency of the spatial frequency U. First, to model the relative sensitivity R as a function of the ratio Ls over S, we observe its trend from our measurement. First, at the left limit, when the sinusoidal patterns are brighter than surroundings, R becomes a linear function. And at the right limit, when the surroundings are brighter than sinusoidal pattern, R becomes a quadratic function. We found a regression model which has those asymptotic trends with 3 fitting parameters, A, B, and C. Note that this model has simple concave shape curves, so it can help to avoid an overfitting. Next, to model the minor dependency of R about U, we model the fitting parameters B, and C as simple monotone decreasing functions of U. In these 5 graphs, the curve R translates and its slope slightly varies as the spatial frequency U varies. Now, to complete modeling the surround-aware CSF, we turn to definition of relative sensitivity. From this equation, we can represent the surround-aware CSF as this formula. We already modeled the relative sensitivity R, so the only remaining part is the rightmost term. Note that this remaining part is the same as a traditional CSF, which does not depend on surrounding luminance Ls. Therefore, we decide to use Barton's 92 CSF model, denoted by S subscript B, as the remaining part. The Barton CSF model has been used for HDR application well. such as popular Dolby Perceptual quantizer. Using Martin's model as our starting point provides backward compatibility to the renowned model. Finally, our surround-aware CSF model consists of our novel model for relative sensitivity R with 6 fitting parameters, and traditional Barton CSF model with fitting 3 parameters to our measurement. However, we found that to apply our model to application methods, we would better to use the practical model rather than the full model. Our practical model for relative sensitivity R is driven by dropping dependency of U to avoid the potential risk of overfitting at unmeasured frequency range. Also, to achieve backward compatibility to existing CSF model, we use Barton's CSF model without parameter fitting, but only with introducing scale adjustment constant. Here are our modeling results. The top row shows fitting results for our full model, and the bottom row shows fitting results for our practical model. Dotted lines denote our measurement, and solid lines denote our fitted model. At the low values of spatial frequency and stimulus luminance, we can see that our full model provides a better fit than the practical one. Also, the full model records a better RMSE error value as goodness of fit. However, the generalization error, computed as the difference between train set and test set errors, has smaller value for the practical model. And next, we will introduce our application. Many famous image processing methods are based on CSF because CSF tells information about how people recognize intensity differences from images. We will introduce several proof-of-concept research of 3 application methods using existing algorithms, but just equipping our surround-aware CSF model instead of existing CSF models. First, we will introduce HDR tone mapping results based on Montiuk's algorithms. Next, HDR video compression based on HEVC codec with transfer function generated by Miller's algorithm, and visual difference predictor, as known as HDR VDP, based on Narwaria's algorithm. This is tone mapping results. We first compare Montiuk's original method, which is based on Dali's CSF model, and compare with ours. This is tone mapped image result from Montiuk's model, and this is result from our model. Comparing this, for the scene with dark surrounding luminance, our CSF represents a low sensitivity. Therefore, it compresses contrast better. Thus, it leads to cleaner images with less residual haze. We also compare existing surround-aware CSF developed by Barton 2003 and ours. First, this image is obtained by Barton's CSF model, and this is our result. We can see our CSF provides more clear image with less haze. And we can also apply HDR video compression using our CSF model. Note that all results in this video are tone mapped using our CSF model. This is original video without compression. And this is compressed video using our CSF and about 1,000 times less size. Finally, this is comparison between visual difference predictor obtained by HDR VDP 2-2, which is based on Montiuk's CSF model, and our result based on our CSF model. We can see that our results provide less wavy artifacts, which is closer to the subjective map. In conclusion, we did a psychophysical experiment using a state-of-the-art HDR display. Our experiment and CSF model takes both stimulus and surrounding luminance into account. We derived our full and practical models of surround-aware contrast sensitivity functions. We presented 3 existing HDR application methods: tone mapping, video compression, and visual difference predictor by plugging our CSF model to existing methods. our proof of concept results provide potential of improvement by scene adaptive approach. Thank you for listening.
Thank you for this nice presentation. Let me kick off the Q&A by asking about the contrast sensitivity, because contrast sensitivity might vary between users or also between gender. Did you test the contrast vision of people before you did your experiments, or did you look into any gender differences?
We tested 13 participants in total, and we have about 3 female participants. So I think it is difficult to some gender trend for some 3 female participants. So some investigating some gender trends will be some good future work.
Right. Holly also mentioned that the contrast sensitivity also changes with age, so you might also want to look into this in the future. There's a question by Gurpreet Singh. Can you please reiterate what is making your metric better with regards to HDR VDP2 metric?
Then can I should I screen share one more time, or just explain?
I think you can share the screen.
So HDR VDP2 results generate some artifacts which cannot be visible from participant, but our results provide some not noisy effect. And also we have another scene for backup slides. I'm sorry. For that scene, we can see more noiseless one, and also we are trying some modeling CSF model, and also trying some application 3 application methods for. So we could not did some quantitative comparison. So our paper contains qualitative comparison. We will append the quantitative comparison for CGF version.
Nice. So if there are no more questions from the audience, I would say let's thank the speaker again.
Thank you.
And we move to the last talk in this session with the title Stereo Inverse Brightness Modulation for Guidance in Dynamic Panorama Videos in Virtual Reality. The authors are Steve Gregoric, Jan-Philipp Tauscher, Nickel Heesen, Susana Castillo, and Markus Magner. The presenter is Steve Gregoric.
Okay. Okay, hello. I hope everyone can hear me well. As this is a bit of a lengthy title, I want to try to break up the title a bit throughout my talk, and I want to start with what we do mean with guidance in virtual reality. And so imagine you're putting up your VR headset, get beamed into your virtual environment, and might be looking at the tree here on the left, because maybe they're sitting a little bird. But the storyteller of this virtual environment might want you to look at the mountains back there in the background, because some sort of story that you want to tell. And here comes guidance, or in our case, more explicitly, visual guidance into play. And what might this be useful? So for example, for unexpected detail that you might overlook otherwise, like the second moon that we have here as seen from our moon. Or there might be just too much information so that you don't find the right information in between all these activities, as can be seen here, while we actually want to find Wally, as we can see here up in the postcard, who's hiding somewhere in between all the other guys right here. And we investigate how we can increase or guide you as a user towards these regions without putting in there such bold black arrows like shown here. And this is where the technique stereo inverse brightness modulation comes into play, which we have actually presented in 2019 on SMSOP. And I just want to give a quick recap of what this method was about. So imagine you're looking at this black ring on a screen in front of you, then typically or naturally both of your eyes will look at the very same black ring. But in a VR headset, this is not the case. So you're still looking at these through these two little displays in front of your eyes at the same ring, but it's more two different representations of the same ring. And if we now simplify this a bit and change one of these rings to another shape, like for example, square, then this two different shapes that are virtually placed at the same place in the virtual space around you causes an effect in your visual perception. It's called monocular rivalry. And we want to exploit this, but not with such geometric shapes, but with brightness modulation. So we will basically for one eye increase and for the other reduce the brightness of the original image. And the nice thing about this stereoscopic approach is that due to this conflicting effect in our perception, that kind of increases the actual or strength of the artifact, we can very much reduce the effect per image. So as we can see now, the both stimuli in the left and right images at the top, you can only barely see the effects up there, while we can still very clearly see the difference in the image below. And this is kind of a comparable effect that appears when those images are kind of overlaid in our visual perception in these stereoscopic environments. So this allowed us to use intensities or pair image intensities below previous state of the art without using any kind of temporal modulation. So now the previous paper that we've presented was only about static images, and now in this paper we have investigated this for dynamic videos. So basically, if it's also working with movements around us. And for this, we have selected a very wide range of different virtual environments. As we can see here, we've picked in and outdoor scenes, scenes during bright daylight and night, and even some underwater settings, to have really a wide variety of different settings for most possible generalizability of our results later on. And moreover, we have used two very different VR systems during our evaluation. One is the HTC Vive and one is our custom-built dome projection system. You probably all know the HTC Vive, which has kind of decent resolution per eye and a field of view of kind of up to 110 degrees. And the dome projection system has kind of a really nice resolution. But the very nice thing about this system is that it at least horizontally offers almost our full field of view. Both systems were upgraded with eye tracking using the Pupil Lab system. So we can see here for the HTC Vive and here for the stereo shutter glasses for the dome projection system. And now for our study, we did actually 3 experiments. The first was more like an initial experiment to see whether this very subtle stimulus will work at all in video, so in moving environments. Then the actual main experiment, and then afterwards we did a 3rd experiment to test if we can use this even to guide users outside the initial field of view, so to even induce head rotations instead of only eye movements. Okay, so the general procedure for all the 3 experiments was basically the same. It was always a free viewing task, so our participants had 20 seconds to freely explore those video environments. And for each of these video scenes, we have manually selected a kind of target region where we wanted the users to look at, which was the same region per scene for all users. But of course, the order of the presentation for the panoramas was randomized for our participants. Then for our evaluation, we recorded the time the participants took to reach the target region and the time they spent fixating on this region. For the first experiment, we only used half of the scenes and only the HTC Vive, as I said, really kind of an initial test to see if this works at all with motions instead of just static images as before. And when just looking at some condensed results, we see here in blue the fixation time on the target region without the stimulus, and in orange with. And we can see that it was significantly increased when using the stimulus. And the same applies for the number of fixations. So they did not only look longer on the target region, but we also managed to have them look more often on the target region. So the stimulus might or seem to be also working within video environments. In our second and the main experiment, we've used all the 13 scenes, while 12 scenes were used for the actual experiment, and the 13th one was used during the instruction phase. We've tested 2 different intensities and stimulus sizes, so in total 4 parameterizations, and both of the VR systems. And again, without going into too much detail here, first looking only on the very first fixation per trial. So when did the participants look first at the target region, we see that this was more often the case that participants reached the target in the dome system as compared to the Vive. So the used system seemed to have a significant influence here, but we were not able to actually show a difference between the tested parameterizations. So this might be something for our future work. And then the same basically applies when also looking at repeated fixations. So when people looked to the target region away and then back to the target region. Also, this was available or happened more often in the dome environment than in the VR headset. And also here, no significant difference for the tested parameterizations. So we can say that the tests or the used VR system should be taken into consideration when using such a subtle stimulus for VR guidance with videos. Finally, in the 3rd experiment, we again used all the videos and kind of modified the stimulus a bit to not directly guide users towards the target area, but we kind of implemented a stepwise approach that positioned the stimulus not directly on the target region, but just in the far outer region of our peripheral vision, so that it's kind of still visible within our current visual field to grab the attention. And then as soon as the participants approached, or the gaze of the participants approached this region, then the kind of intermediate position was updated more towards the final target region, so that we kind of stepwise guided the users towards the final target region. And again, without too much details, here, again in blue without and in orange with using the guidance stimulus, we see that for both systems, the headset, Vive, and the dome system, the stimulus was able to significantly increase the target fixations, both in terms of, again, fixation time and number of fixations. So these stimulus can even be used to guide users outside their field of view. So we can even induce actual head rotations, not only eye movements, using the SIBM stimulus. Okay, that's already it. Let's take a quick wrap up. So we don't want to miss important information accidentally. We always want to find the right information if there's very many information around. We want to try this using the SIBM stimulus because it can be used with very, very low modulation of the original image, so it's not very disruptive from the original shown content. We have tested this using the two very different VR setups, and we're able to show that it's successful in a very wide variety of different virtual environments. And that's already it. Thank you very much for your attention.
Thank you for this very nice talk. I was wondering, did you look into whether the location of the stimulus has an effect on the attention of a user? So if it's very close to the viewing direction or farther apart?
So we actually did not investigate this, but so for the first two experiments, or mainly for the main experiment, we just used regions that were in the kind of full field of view, so that the stimulus basically even, or at least had a chance to grab the attention somehow. And we kind of evenly distributed this between kind of just barely outside foveal vision, or a bit more. I think it was between 30 and 90 degrees. So evenly distributed with this kind of range of angular offset from the initial viewing direction, which was kind of always straight ahead at the beginning of the experiments. And then for the third experiment, we used stimulus positions above 90 degrees. But we did not really test it whether it would be faster if the stimulus is closer to the viewing direction right at the start. But I would think so.
Mm-hmm. And if you have moving objects in your video, they also grab our attention, right?
Yes.
So do you have any thoughts on how this competes with a stimulus that you present at a different location and at the same time when you have a moving object in the field of view of the user?
So as I said in the beginning, we presented the stimulus in the beginning of, or the earlier, just for static environments. And we just saw that we really had to kind of increase the stimulus, either size or intensity, to still grab the attention of our participants. So for the videos where there was some moving objects around, we had to use kind of a stronger stimulus compared to static images, which is kind of intuitive.
Yes. So we have some questions from the audience. Omer Shapiro asks, can you talk about the scenes used in the study? What was their simulated contrast, daylight, indoor?
So I can't really tell maybe not.
What kind of variations of scenes you used?
So we've tried to kind of grab basically all possible kinds of, or most possible kinds of settings. So really try to find some bright and dark indoor settings, and then again some daylight, very, very bright, and very kind of midnight dark outside settings. We also used scenes that were very wide open outside field settings, and also then some indoor settings where objects are really close to the viewers. So we try to compensate for most of things that might possibly come up in the future as potential application surroundings.
Okay, we have another question. Very interesting work. Would the use of the SIBM stimulus lead to some sort of visual fatigue if used repeatedly? And did you run into any experiments in this direction?
No, we did not investigate visual fatigue, but I think it should. So I should add that we used kind of gaze contingent deactivation. Let's term it so. So we deactivated the stimulus once the user really approached the target region. So that kind of does not, or there's no chance of annoying the users once the kind of guidance was successful. and there's basically no reason to guide them there again. As I said, we didn't precisely investigate museum fatigue, but I think as we did not, like many other approaches, had any kind of temporal modulation in there, it should not really be that much of annoying.
Okay. I also have another question. Did you consider using your method to assist people with some form of vision impairments? Because people with low vision are often afraid to miss something, especially when trying VR simulations. So did you look into this, or did you think about that?
Yeah, so we thought about that, but I think that's kind of not the audience for us, because I think in those cases it would really be better to have kind of these rather bold guiding mechanisms, like shown in the beginning, with kind of maybe an arrow or really kind of a border drawn around the objects of interest. I think we are more concerned about, let's say, virtual museum tours or something like that, where you really want to change the object that you can see or that you can look at as little as possible. So to really kind of, if possible, do not change their appearance at all in the best case. Mm-hmm. So I think it's maybe kind of a different target.
Okay, thank you. So if there are no more questions, let's thank our speaker again. In fact, all the speakers in this session. Next up is the keynote by John Barron, which will start at 5 p.m., so in a few minutes.
Okay, I guess we can start. Just checking that it is okay. Yeah. So it's my pleasure to welcome John Barron to give this keynote at EGSR. So John did his PhD at UC Berkeley with Jitendra Malik. So that was thanks. So he was in the computer vision group. For the anecdote, I was a postdoc at the computer graphics group at the time, and I remember him sneaking in the corridors. So I guess he was already interested in graphics at the time. And so one of his contributions during his PhD was one of the first methods capable of estimating jointly shaped material and lighting, so a form of inverse rendering from a single image. Afterwards, he joined Google, where he worked on various projects, including Google Jump and the HDR+. And recently, he contributed to this NERF revolution, which is really attracting a lot of attention, including papers that we saw in the program this week. And I think that will be the topic of this talk. And I will conclude by also mentioning that John received a number of awards for his research, in particular the PAMI Young Researcher Award. So John, I'm looking forward to hear your talk. The stage is yours.
Thanks, Adrian. It's a very nice introduction. Hi, everyone. Thanks for coming. Thanks for the invitation to speak here today. Can I just first get a confirmation that my slides are visible and my audio sounds okay? Is everything? I heard a little thumbs up sound. Is that okay? Cool. Great. So yeah. So as we were just told, did my PhD at Berkeley, doing computer vision stuff, and now I'm at Google. I've been at Google for a long time now, and I lead a small team of people who are just investigating NERF. Some of whom you might know or have seen before, and it's mostly their work that I'll be talking about today. And yeah, I'm very much a computer vision person. I don't really have a graphics background. I'm kind of a computer vision person who works on 3D reconstruction and low-level type things. So in the eyes of most computer vision people, I'm an outlier because I don't work on recognition, and I can kind of communicate with graphics people, so I'm kind of at that interface, but I'm definitely not a graphics person, and I'm really hoping that this is a good opportunity to get some feedback from hardcore rendering people and see what we're missing and what we can do in this space. And I'll mostly be talking about NERF. Quick check, can someone tell me what the frame rate looks like on the upper right there? There's a nice video playing for me, but I'm not sure if it's just a bunch of still images for everyone else. Okay, thumbs up I guess means it's kind of like a video. Throughout the talk, I'll just be showing videos that to me look really nice and to you might not look nice depending on how the streaming is working. So NERF. NERF stands for Neural Radiance Fields. Neural because there's going to be a neural network, although it's actually a pretty minimal component of the system. Radiance fields because what the neural network will be modeling is a field of radiance. So here field is kind of in a calculus sense, as it's like a smooth thing that exists in some 3D space. And radiance is what that field is going to be modeling. Radiance here means kind of glowing light. So emitted light going out from some point in space. And we started using this for view synthesis, but it's kind of become a more general purpose technology. This project started as a collaboration between Google and Berkeley, and now a lot of the authors are, the student authors are at Google, so it's kind of been moving towards Google. So this is the problem that we first set out to solve. This was the problem of view interpolation. We want to take a sparse sampling of views, so 10 or 100 images of some object, and turn them into a model from which we can then produce new renderings of that scene from different angles that weren't previously observed. And it works really well. If this video is not super compelling on your end, feel free to follow the project link there, and you'll see lots of video assets of the things I'll be talking about. And NERF builds on kind of two recent trends in computer vision and machine learning. And one of them is kind of this rise of use of volume rendering for view synthesis in computer vision work. And the best representative technique kind of in this line is these multiplane images, which take an image and kind of promote it to a multiplane image, which is like a kind of a camera frustum that you've divided up along the z-axis, and you're putting colorful and
alpha transparent like slices of the 3D world on each of those planes. And you can imagine if you can do that successfully, you can then make new views by moving the camera slightly and kind of collapsing the camera frustums down. And this works really well. These techniques produce really nice looking images. They're fairly realistic. And this technique has this really nice advantage that it's very well behaved for optimization, because volume rendering is just a really nice fit for gradient-based optimization. And there's a really big problem with these techniques, which is their storage requirements. Because you can imagine if my solution to doing view synthesis is to take an image and turn it into, say, a voxel grid, and I want to make, megapixel sized images, then I'm going to need at least a voxel grid that's 1,000 by 1,000 by 1,000. And then if you keep pushing on that, you see that these techniques to kind of scale will require more memory than you could ever hope to have in a computer. And that's kind of like the limiting factor for these techniques. And there's a separate thread going on in the machine learning community, which is the use of neural networks as continuous shape representations. So normally people think about neural networks as like you have a function approximator that's going to map input to output. So you're going to have an image that comes in as input, and the output will be a label of that image. This is a very different and kind of unusual way of using a neural network. Here, the input is a coordinate. We started calling these models kind of coordinate-based methods for that reason. So the input is some point in space, like an XY position on an image or an XYZ point in 3D space. And the output is something like whether or not that point is occupied, or how far away that point is from a surface, or the color and the density in the case of NeRF. These techniques are really cool for a number of reasons. The main thing that they really offer is that you can have this tiny neural network that can basically express almost anything, because neural networks are just they're universal function approximators. They can basically learn any mapping, and they can do that using very few weights relative to kind of brute force solutions. And the shortcoming of these works is that they don't really provide a way to generate images kind of natively. They provide ways to represent shapes, and you can try to render those shapes, but if you do that, the optimization becomes tricky for a variety of reasons. So NeRF kind of sits at the intersection of these two ideas. Here is the neural network at the core of NeRF. It's a very boring neural network. It has 9 layers, 256 channels. It's a ReLU activation. It's straight out of 1985. There's nothing going on here. The input is 5 numbers. So XYZ, a point in 3D space, and a viewing direction, theta phi. So that's the direction at which you observe that point in space. You can ignore the theta phi for the most part and just think of it in terms of XYZ. And the output is 4 numbers. So 3 of them are color, RGB. What color is that point in space? And the 4th is density, which we'll call sigma. And that's a number from 0 to infinity. And that is how dense is that point in space. This neural network, we're going to repeatedly ask it, here's a point in space. Tell me about it. Tell me what the color is, what the density is, and it will return a result. This neural network is wrapped inside of a ray tracer, a kind of like straightforward but a little unorthodox ray tracer. So we're going to have a bunch of cameras. We're going to assume that the location, the pose of all the cameras is known. Say it's provided by the user, or it's from the structure from motion package, or the data synthetic in this case. And for each pixel in each of the images, we're going to shoot a ray from the center of projection of the camera out through that pixel, and it will travel out into the world. And then we're going to draw samples along that ray. We're just going to evenly draw XYZ coordinates that lie along that ray. And we'll take all those XYZ coordinates and push them through the neural network. And here I'm assuming we have a trained NeRF. The NeRF, the MLP at the center of this will produce as output a bunch of densities and colors. And then we just do straightforward alpha compositing. We walk from the back of the ray up front. And if things are dense, then they partially occlude the thing behind them, and we keep marching all the way up until we have a color that's just a color for that pixel, and that is the rendered color. And then we move on to the next pixel. That's the whole rendering procedure. It's very straightforward. And the really nice thing about this volume rendering approach is that it's super well behaved in terms of gradient-based optimization. So if you write down kind of straightforward volume rendering system based on kind of unevenly spaced particles. This is, I think, from Max 95. You can write it down, and you'll discover that you can basically implement it in PyTorch or TensorFlow or JAX or whatever, using all the ops that are already there, and they're all like very nicely behaved ops. You get a bunch of sigmoids and cumulative sums. So this just works. It's very straightforward to do gradient descent on in this space, and it's very well behaved. And what that means is that we can train a NeRF by we initialize the weights of this MLP to be random, and we just render that these random weights. We get a bad-looking image, and we measure the difference between that rendering and the input image, and we minimize the squared error. So we just backpropagate that residual onto the weights of the neural network. And you do this a billion times, and you will get a set of weights that have that describe the geometry, or really the density and the color of the scene well enough that you can get photorealistic renderings out of it. And I should note that the reason we're doing volume rendering here is not because we think that our scenes are volumetric. And almost all the results you'll see, the scenes are definitely not volumetric. This is purely just because of gradient descent. That is the reason, the motivation for this setup. So we'll take a bunch of images of an object, and we'll give it lots of, we'll supervise the pose, and we'll just do gradient descent, and it works. I mentioned that viewing directions are available as input to the network, and what this means is that the model is capable of recovering non-Lambertian appearance. So this is a really, I would say, a pretty weak aspect of this model, because there's all it has access to is the viewing direction. It doesn't understand anything about surface normals or geometry or materials or lighting. It's just kind of a neural approximation to the distribution of outgoing radiance from a point in space as a function of angle. But it is sufficient for surprisingly compelling specularities and non-Lambertian effects. So let's look at some results. So these are, again, they're all going to be better viewed probably on the project website. But you can see that NeRF is able to do a really good job of recovering complicated geometry, shiny materials, thin structures. Here there's glass with water in it, and it kind of looks like it's refracting. There's really no reason for that, but it's able to fake it. Here we have a pond that looks like a mirror, and it can fake that by putting a copy of the world below the water. So it works. It works really well. And it's particularly striking in comparison to kind of prior work in this space. This is kind of the state of the art in like the neural rendering space at the time of publication, and you can see there's a very significant difference between what NeRF can do and what SRNs can do here. And here is an evaluation against the state of the art on kind of the classic, more graphicsy 3D vision side of the work. As you can think of this as the kind of spiritual successor to unstructured lumograph, light field rendering type techniques. And I don't know what this looks like over the stream, but still images from these techniques often look fine, and there's a lot of popping and jumping as you kind of change the set of nearest neighbor images you're kind of using for these techniques. One cool side effect of this approach is that we're able to describe really complicated, interesting looking objects using the weights of a neural network that it's very small. It'll usually, I think in all these experiments, the neural network has 2.5 megabytes of floats as the weights, which is about a factor of 6,000x compression compared to the input images that were used to train these techniques. So this is also like a very effective, in addition to being a nice technique for view synthesis, this is a very effective compression technique. The view-dependent effects are fun to look at. So on the left here, we're just moving the camera as usual, and you can see the specularity on the stove moves around as you'd expect. And on the right, we're not moving the camera, but we're telling the model that we're moving the camera. So we're probing it for the view-dependent directions that correspond to other angles while keeping the actual camera fixed. And you can see the specularity on the stove moves back and forth as you might expect. And again, I should say this is a very crude approximation to how materials and light actually work, but it's sufficient for a compelling illusion. And so these NeRFs feel kind of magical in some way because there's like a neural network that's kind of a mysterious black box. And I just want to stress that the neural network is doing something very boring. It's just mapping from a coordinate to a density and a color. And as such, it represents a model of geometry that is a sort of straightforward model of geometry. And you can do things to it like you would to other models of geometry. And in this case, what we're doing is we're shooting rays at the scene, and we're going to measure the expected termination depth of each of those rays. So the mean of the alpha compositing weights, or the expectation with respect to the alpha compositing weights. And we're just showing that on the right here. And you get these really wonderful looking depth maps that have lots of nice thin structures and detail, and none of the kind of fattened edges and weird over smoothing artifacts that you're used to seeing in stereo. And these are good enough that you can use them. You can use them for object insertion, and the effect is compelling and somewhat believable, although the sphere is not particularly realistic. And you can do things like mesh them. Although this was the thing we did immediately upon submission. We kept working on this aspect of this model, and we were able to eventually get it to the point where we could take a trained NERF and not just mesh it, but produce a full, like a complete rendering model, or a complete model of the scene that you can render in real time in your browser. So there's a link at the bottom, nerf.live. Feel free to open up a tab and try it out. Click on the demos tab. And it should run at 30 frames per second on your laptop. The fan will probably spin up and it'll probably get a little hot, but it should work. And this is just taking a pre-trained NERF and kind of baking it down into normal graphics primitives, like there's a sparse 3D grid with texture atlases and things like that. And there's some small amount of neural magic with how the view dependent effects are rendered. And if you don't feel like opening up a tab, here's a recording of me just playing with it. And it works. It's good enough that you could use it for a lot of things. And yeah. Now, the bad news is that the system I just described actually does not work very well if you implement it exactly the way I described it. The system I described will produce slightly over smooth results. And there's this one weird trick for getting this to work in practice. And to explain this weird trick, it's helpful to kind of back off from NERF to you can think of this as a dramatic oversimplification of NERF, but I think that's a bit too generous. This is just a toy problem where you're going to train a neural network that maps from a pixel coordinate, so XY, the XY coordinate of a pixel, to the color of that pixel. And this is a weird thing to do. You probably should never do this, but if you did do this, you might be surprised to see that it doesn't work. So if you train a neural network to just memorize an image, it doesn't need to do anything particularly complicated here. It just needs to memorize all of the values you've given it as input. A neural network will struggle to do this, and you'll get these kind of over smooth, sort of polytopy looking results. And this is weird because neural networks, in theory, can do anything. They're universal function approximators, and there's more weights in the network than there are pixels in the image in this case. But it can't do this. And there's this one weird trick for making this work that we discovered, which is that instead of passing in the coordinate, like the XY coordinate, you pass in a transformation of that XY coordinate where you just pass it through a bunch of sinusoids. So sine and cosine of the coordinate, and then twice that and 4 times that, etc. So you have these higher and higher frequency sinusoids. And this is just this fixed function that you apply to the coordinate before you feed it to the neural network. And just doing this one thing makes this work. So now we can just memorize an image. That's what you see on the right there. And it comes into focus immediately as opposed to this without this trick. And this works in 2D. This also works in 3D for basically the exact same reasons. Applause. Okay, cool. Thanks. So we were really confused by this when we were working on NERF. And for a long time, we thought we couldn't submit NERF anywhere without understanding this, but we decided to go for it anyway. And that was probably a good call. But we immediately set out trying to figure out why this was happening. And this led us to a paper that this was at NERPS this past year. And this was kind of a theory paper on what's going on here. Why is this happening? And I hope this will be of interest to this audience. Maybe people here are not super excited about the idea of an ML theory paper, but in practice, what this paper did was it showed that what's going on here is just very basic signal processing and interpolation. And it kind of demystified these neural networks for us. And hopefully it'll do the same thing for some people here. So the title of the paper is the takeaway. So Fourier features, these sine and cosine embeddings of these coordinates, they allow neural networks to learn high frequency functions with lots of high frequency variation in low dimensional domains. So 2D, 3D, etc. So here's like a cartoon visualization of what this whole NERF thing is doing. You have an input coordinate V on the left there, which is a very short vector. In NERF, it's 5 numbers. It could be 2 numbers in 2D. And then you feed that input vector to a fixed input function gamma. And for NERF, that was positional encoding, which we've written out here. And this takes V and projects it onto a bunch of axis-aligned sinusoids that are frequencies or powers of 2 from each other. And you feed that positional encoding into a boring ReLU MLP, and you get the output, which is, in the case of NERF, a single color and a density. And this positional encoding function has a single hyperparameter that we noticed was like super important. It's this L value here. And it's shown in a little red box. And that determines how many levels there are in this positional encoding. and also, of course, the highest frequency that gets used. It's the maximum frequency. This was the knob we used for regularizing NERF. If things were too smooth, we would make this number higher and it would come into focus. But if you made it too high, you'd start seeing noise and floaters, which was confusing to us. But after staring at this for a while, we realized that this positional coding was kind of overly complicated, and it's better and simpler to just use random Fourier features. So we can instead generate this big random skinny matrix B and project V onto it and push that projection through a sine and a cosine. And this is a classic technique for kernel machines and straightforward discriminative machine learning. And there's lots of nice work on these sorts of features that we can take advantage of. The classic citation is Rahimi and Recht, which is a really wonderful paper. These random Fourier features also have a hyperparameter, and that's the standard deviation that you use to generate the matrix. And this serves the same sort of purpose, because in both cases, it kind of determines the maximum frequency that you're going to see. So to understand what these Fourier features are doing, we found it extremely useful to bring in ideas from this neural tangent kernel literature. For those of you who aren't familiar with this, NTK is this really remarkable result that shows that trained neural networks are basically equivalent to special kinds of kernel regression. This is a particularly wonderful result if you're not super excited about neural networks and you'd rather work on kernel regression. You can just take this result and say, oh, actually, it's the same. It's all the same, and nothing's too scary or weird. So a quick review: kernel regression is a classic nonlinear regression algorithm, and you can think of it as basically a way to produce output predictions by taking a weighted combination of the labels in your training data. So you use some predefined kernel function, like Gaussian distance between 2 points, and you use that to measure the similarity between an input and every training data point you have, and you get those weights, and you take a weighted combination of the labels of all your training data, and that's your prediction. It's very straightforward and intuitive. The really surprising thing about NTK is that if you work on the math for a long time, you can show that the fully trained neural networks are all technically doing kernel regression, just with a very unusual kernel. In practice, this is not a super useful observation most of the time, because kernel regression is very slow and hard to use. You need a matrix that has as many rows and columns as there are data points in your data set. So 1,000,000 by 1,000,000, and then you need to invert it. It's kind of uncomfortable. But as an analytical tool, it's super helpful for understanding why neural networks are doing what they're doing. And another fact from the NTK literature is that for ReLU MLPs, the kernel that the neural network is using is a kind of dot product kernel. So if you're using a normal MLP, what you're basically doing is taking a dot product of your input with all your training data and then pushing that single scalar dot product through a nonlinearity. And when your input is high dimensional, which is almost always how neural networks are used, this is actually a totally reasonable kernel. This works fine. And the problem is when your input is low dimensional, like in our case, you can see why this might be problematic, right? If I'm trying to interpolate into an image, if you're trying to design an interpolation algorithm, and all you have to work with are the dot products between your target pixel and all the other coordinates in the image, you would have a hard time writing that algorithm. It would be a very awkward thing to do. And if you were in that situation, you would say, I don't want to do this. I want to do interpolation with like a stationary kernel, right? I want to take my point and I want to measure the distance from that point to all the other points and then throw away the distances that are very large. This is just classic signal processing. This is what everyone would do when designing an interpolator. So, okay, so now let's put these ideas together. So here's the dot product of Fourier feature inputs, just written out from the definition. And then you can apply a simple trig identity and you get this. And you can see that the dot product of Fourier features of V is actually a stationary kernel with respect to V. So it's shift invariant. It just depends on the distances rather than dot product. And this is not, this isn't a particularly new observation. This is just standard math, but it's very critical for this task. So now we can put these two pieces together. So we know that our neural network is basically a kernel machine based around dot products of its input. And we know the dot product of Fourier feature mapped inputs is a stationary kernel. So this means that composing a ReLU MLP with Fourier features gives us a new kind of neural network that corresponds to a kernel that is stationary. And so now it makes sense why this would be a good idea or even a necessary idea, because we know from signal processing that stationary kernels are what you want to use when you're doing interpolation tasks. It's just the right choice. And you can take this idea even further and notice that because our training data are these densely and evenly distributed points in a low dimensional space, the output of this Fourier feature network is effectively a convolution with weighted deltas at each training point location. And this nicely parallels how you would solve an interpolation problem using classic tools, right? You would define some stationary kernel like bilinear interpolation, and then you convolve that input with the kernel to get a smooth interpolated output. So basically, this Fourier feature trick is just a way of turning MLPs into interpolating machines that behave the way you want them to behave, or behave the way you would design a system to behave from first principles. So here's what this looks like in practice. This is that same 2D image memorization task that I showed earlier, except we have separate training and test sets of the pixels, so we have to worry about overfitting in addition to underfitting, unlike what we saw before. So here is the output of the network on all pixels, training and test, and the Fourier feature scale is set to 4, just a particular value that works well. And so the image on the left looks good, it looks like an image. And on the right, you can see this, now we're visualizing a 1D slice of the composed NDK, the kernel that we know this model is using. And you can see the kernel looks sensible, right? It's large at 0, and it's small far from 0, and it kind of falls off like a Laplacian or a tent kernel. And this all makes sense. This is what you would do if you were designing an interpolator. Now here, I've set the scale parameter of the Fourier features to be very small, and this is similar to having no Fourier features. So like before, you can see that the output of the network is heavily oversmoothed. And if you look at the kernel on the right, you can see it's very wide. This all makes sense. If you were doing interpolation with a very wide kernel, you'd expect really oversmooth results, and that's exactly what's happening here. Now I've done the opposite and set the scale parameter to be very large, and this produces an image with a lot of noise. Maybe it's been denoised by the stream. And in the middle, you can see the trained PSNR is very high. The test PSNR is very low. That's just overfitting. And on the right, you can see the kernel, which is an absurdly narrow kernel, right? It's a delta function with a bunch of noise. You would never want to use this for interpolation. So looking at all this together, you can see that when you're using these Fourier features, the scale parameter of this fixed Fourier basis gives you a sort of knob that you can tune that lets you balance between underfitting and overfitting. And this exactly corresponds to the NTK perspective on the problem where you have this stationary interpolating kernel that you're modifying the bandwidth of. So we were using this idea for NERF, and it worked well, but we realized we could apply it to same sort of to a wide range of problems that you see in computational imaging or 3D vision. So here's a bunch of setups where we have like a single scene or a single set of observations, like pixels in an image or 3D occupancy or even MRI scans. And you can try to solve these problems by just training a neural network to overfit them, and you'll get results that look oversmooth and not particularly good. But for all these tasks, if you just add in a Fourier feature mapping to the input, suddenly this naive baseline of trying to solve MRI scanning or image super resolution by just having a neural network memorize the input, it becomes a reasonable idea. It's probably not how you should get your brain scanned, but like it works, right? The image comes into focus, the dragon gets its details, the MRI looks like a brain, and NERF works, as we saw. It's super easy to use. Here's a layer in a neural network, and here it is with Fourier features. It's a 2-line change, so it's very easy to try out. And you should try it if you're working in these problems, or really you have to try it, because if you don't try this, we know, like we can prove that you will get oversmooth results. And I just want to clarify that, like, this is a very unmagical result. People see neural networks and they think like, there's a lot of, there's something fancy happening here. So there's a neural network that's learned something, and it's going to generalize and impose all these other things. And most people see that as a positive. A lot of people see this also as negative, like they don't want these complicated black boxes. And I just want to clarify that that's not what's going on here. There's very little magic here. These coordinate-based neural networks, they're really just lookup tables. They behave exactly like lookup tables, except that the kernel is a kind of weird neural thing with a little extra wobbling you might not want. But the really nice thing is that you can have a very, very large lookup table, like say like a 7-dimensional lookup table with extremely high resolution, right? Because these neural networks can describe basically anything up to the bandwidth of that kernel. And you can never fit a 7-dimensional lookup table that's 1,000 by 1,000 by 1,000, et cetera, in memory. But you can have a neural network that takes maybe a few million floats to store, and it will be able to describe that just as well. So this is hopefully is a useful takeaway. Now I just want to back up a couple of levels and talk about like what all this means and like what are we doing here. Like is this a question I get a lot is like, is this neural rendering? Are you doing neural net rendering? And I don't totally know, because the meaning of this phrase is kind of changing over time. It kind of has 2 meanings, and I think it's worth describing them and kind of drawing a contrast between them. And the older paradigm for what neural rendering means is this idea that the rendering is done by a neural network. So this neural network is this weird black box that takes in some input, maybe like a proxy geometry or a semantic segmentation map, or even just a label that says face or dog. And the neural network does a bunch of magical stuff under the hood and produces as output an image. It directly renders an image. And this works really well. These techniques are quite mature. They are quite effective for a lot of tasks. They have some problems with stability. It's very hard to get kind of stable looking results out of them because the input must also be stable, and that's kind of a limiting factor. But NERF is doing something very different from this, right? Like this is a totally different way of looking at this problem. And here there's still a neural network. It's still a magical black box, but the neural network is not doing any rendering. The neural network is parameterizing the world. It's parameterizing a particular scene in the world, its radiance field, and it is rendered by a very boring, normal-looking rendering engine. I mean, it's not super normal because it's implemented in a differentiable programming framework, but it's the rendering engine is all very straightforward. It's determined by physics. You can look at it and understand it fully, and it's real. It's determined by physics. There's no kind of hand waving in the rendering part. All the hand waving is in how the model is described. And making this shift where you have this neural component and this rendering component, and they kind of interact to produce a rendering, it seems to be like the big leap to make, or the big leap that NERF is making to get these sorts of results. And the critical aspect of this is that the rendering engine is real, right? We are constrained by physics, so we get to take advantage of all of the things that physics gets you, as opposed to the old paradigm where the neural network has to learn things like occlusion and volume rendering and things like that from scratch, which is a big ask. And another like kind of point of comparison I want to draw is as against kind of other works on differentiable ray tracing, because NERF is doing a very different thing from kind of the mainstream way this problem is being addressed in graphics. There's a lot of work on differentiable ray tracers, and most notably Redner and Mitsuba too. There might be others. I'm actually kind of ignorant to this field. And the way these models work is they take a very good ray tracer, like especially Mitsuba, which has everything in there. It's really great. And then they add gradients to it. They make it differentiable. And I think this is amazing that this has been done at all. This seems so hard, and I'm flabbergasted that people have been able to do this successfully. And this approach is really wonderful in a lot of ways. You get excellent quality because you have a really good rendering engine. Presumably it's been optimized for speed and has a lot of functionality. And then you get gradients on top of that, which is amazing. The problem is that these techniques are kind of built usually around mesh-based scenes. And if you try to do gradient descent on, say, a polygon soup, if I just initialized my world to be a bunch of random polygons, and I say do gradient descent on that to recover these images, like we're doing in NERF, optimization is very poorly behaved. It's really, really hard to do gradient descent on a tri-mesh of a scene because of just so many issues. I mean, just getting the gradients of triangles is challenging. That's a big part of the contribution of Redner and Mitsuba too, as I understand it. And you have things like occlusion to deal with, and gradients will die. Gradients, it's a really hard problem. And NERF is doing something that's really weird and kind of backwards, and in maybe a bad way, maybe a good way. We're using a simplified volume rendering system with these coordinate-based neural networks, and we're kind of building it all from scratch, right? Like this rendering engine is just the thing we could build out of the tools we had. And it has one big pro, which is that gradient-based optimization works super well in this context. Like we get good gradients and we can follow them. And if you just myopically chase the gradient of your loss, you will recover a really good 3D model of the scene. And it has a really big problem, which is that we're basically in a position of kind of reinventing and re-implementing all of graphics from scratch. And I don't think this is necessarily a good thing. Ideally, we wouldn't have to do this, but it seems like when gradients are your first priority, like when you adopt this other paradigm of kind of starting from what's differentiable and what is easy to optimize, then working back towards getting good pictures, you kind of have to turn a lot of these ideas on their head. And for the rest of this talk, that's basically what I'll be doing. So here's a little cartoon history of computer graphics. And so here's NERF. It's built off of really old ideas, ray tracing, volume rendering, multi-layer perceptrons, even like the neural network powering NERF is as old as I am. And these are all like very classic ideas that we're just kind of stealing and modifying and putting together. And we're going to build on this and basically kind of do some bug fixes and some improvements. The first will be kind of modernizing NERF using basic ideas from anti-aliasing. We call this MIP NERF. And the second will be trying to turn NERF into more of a inverse rendering model by building in actual material models and global illumination. And I expect that we will continue kind of pushing this trend and slowly modernizing and kind of patching NERF and bringing it up to speed. Although I'm also like very enthusiastic at the idea of someone coming from the other side of this timeline and just eating our lunch and just figuring out how to get really good gradients or kind of put these two things together. I expect we'll end up, as a community, we'll end up meeting in the middle somewhere. So here is MIP NERF. So this is recent work that we have, and this is basically a bug fix for NERF because there was a really big problem with NERF that took us a long time to kind of really come to terms with. So let's look at what this problem is. So here's a short test set sequence from one of the scenes in the Blender dataset that NERF used, and here is what happens if you render NERF at full resolution. And it does a great job. So the SSIM score is close to 1, as we expect. And but here is what happens if you render NERF from further away. You pull the camera back or you reduce the resolution of your camera. And instead of a nice photorealistic reproduction of the ground truth, which you see in the lower right, you start to see a lot of jaggies, and the SSIM drops a lot. And so you think, okay, well, NERF just needs to be trained on multi-resolution data. But if you do that, it doesn't fix this problem. Performance improves a little at the low resolution, but it drops a lot at the high resolution, which is not ideal. And so our fix, which we're calling MIP NERF, you train it on the same data, and you're able to get high resolution, high quality results across multiple scales instead of just a single scale like we saw in NERF. And it doesn't degrade the performance when you train out multiple scales. It actually just works about the same. So okay, so here's NERF. This is the rendering model for NERF. It renders a whole image just by rendering each single pixel individually. So we can just think about one pixel in isolation. And here is it takes each coordinate along that ray and encodes it with a positional encoding. And if something is not along that infinitely narrow ray, then NERF does not see it. It's just shooting out this very tiny ray that will just basically alias all of space. So that's NERF, and this is MIP NERF. And the first big difference is that instead of casting a ray through each pixel, we're going to cast a cone. Here, the radius of that cone is determined by the size of the pixel on the image plane. So this cone is modeling the whole volume of space that's going to be visible by that pixel. This means when we render the cone, we want to average out all the content within that visible volume instead of just rendering whatever happens to intersect with the infinitely narrow ray that NERF was casting. Now, instead of sampling single points along each ray, we're going to slice up this cone into conical frustums. And here we're isolating one of those conical frustums by itself. And conical frustums are really hard to manipulate analytically. So we're going to fit a multivariate Gaussian into this frustum. And this has a simple closed form solution. It's just a couple lines of code. And instead of positionally encoding a single coordinate along the ray, we're going to compute the expected positional encoding with respect to that Gaussian that we've constructed. So because of some nice properties of sinusoids and Gaussians, this also has a really simple closed form that you can compute very efficiently. And we're going to call these features integrated positional encodings because they're just the integration of positional encoding. So here's what the positional encoding used by NERF looks like. So we have a single 1D coordinate x shown on the left there, and we're projecting it onto a bunch of sinusoids whose frequencies are powers of 2 from each other. And as x moves around, you can see the sinusoids vary. The higher frequency ones very quickly, and the low frequency ones very slowly. Now here's what our integrated positional encoding looks like. And we're modeling a Gaussian now that's parameterized by a mean and a standard deviation. So when the Gaussian gets wide, the encodings at these higher frequencies get shrunk towards 0. And when the Gaussian gets narrow, those frequencies reappear. So by using these features, MIP NERF can reason about the scale of its inputs by just looking at the scale of these encodings. And this lets the model kind of understand the difference between small volumes and large volumes. If we're modeling a large part of space, we fundamentally deprive the model of the high frequency coordinates that correspond to that because they're relevant. You just need to think about the low frequencies. So here's some quantitative results. So accuracy is on the y-axis, lower is better. X-axis is how long it takes to render 1,000,000 pixels, and lower is also better. And here we've plotted NERF. This is actually an improved version of NERF. And this is if you take NERF and you super sample it. This is also a totally viable way to reduce aliasing. You just shoot lots of randomly jittered rays. And you get a much lower error, but you also, things get a lot slower. And this is MIP-NERF, which is about half the error of this NERF baseline, and it ends up being a little bit faster for a variety of reasons. And it's much, much faster than supersampling. And this is all consistent with what you'd expect from normal anti-aliasing work. Pre-filtering is going to be faster than supersampling. So yeah, it ends up being a little bit faster than NERF, and that model ends up being half the size because NERF actually has a coarse and fine model. There's two separate models. In this case, we just have one model that it's like a MIP map. It kind of models the whole thing across all scales. Because it's neural, it ends up being very compact. Here are some results on that multi-scale Blender data set that we've been using. So NERF is on the left and MIP-NERF is on the right. And when the camera zooms out, NERF has a lot of jaggies, MIP-NERF does not. When the camera zooms in, NERF tends to be over smooth and blurry because it's trying to split the difference between two different resolutions. And the only way to do that is to be blurry at one of them and have jaggies at the other. And MIP-NERF just has nice photorealistic renderings across all the scales. Cool, so that's, here's another extension to NERF. That we call this NERV. And the goal here was to take NERF and generalize it to the problems of relighting and material editing. So here's a cartoon visualization of what NERF is doing. NERF models the scene as a continuous volume of particles that basically emit light. The world is just made of glowing fog. That fog might glow differently from different angles, but that's it. It has no notion of where those colors came from, even though they are the product of lights and materials. NERF does not know that. And this is a real big problem if you want to relight a NERF, because there's no way to take this. I mean, we actually do have work where we take a NERF and kind of factorize it out, but natively, NERF does not enable relighting. And there's an easy fix to fix this, or to kind of enable this. You could replace the radiance with reflectance. So instead of modeling the outgoing light at each point in space, you could model the materials of that point in space. And people did this actually very shortly after NERF was out, this neural reflectance fields, where they did exactly that. And it works pretty well. The trick for this, for getting this to work, is that they co-located the light with the camera in all these experiments. And that's a very critical trick for making this to work that we were able to relax. So let me explain why that is. So I'm sure all this is very straightforward to a lot of the audience here, but if you want to compute the color of an array and you have lots of light, you have to think about the interaction of all those points and all those lights. So all the light will shine on the scene, and that will get accumulated and observed by the image, by the camera. And from NERF's perspective, what this means is that when we shoot a ray, we can't just consider the samples along that ray. We have to then take each of those samples and shoot a ray from them out towards each of the light sources. This is obvious. This is the normal kind of reason why ray tracing is expensive in graphics, but it's even worse in NERF, right? Because we don't know where the world is. We can't just shoot a ray and end up at a surface and then bounce off of it. There is a surface everywhere. It's all volumetric. Everything is potentially occupied, and we don't know where stuff is or isn't. So that means when we shoot a ray from each of these samples, we have to query points along each of those rays to measure whether or not the space is occupied or not. This is incredibly expensive. You basically can't do this for a large number of lights. So we thought really hard about how to fix this, and we came up with a trick. And the basic idea is to kind of take the ideas from NERF. So in NERF, we have this multi-layer perceptron that we just ask questions of, and we hope it gives us the right answer, and we supervise it so it gives us the right answer most of the time. We're just going to do the same thing, but for illumination. In particular, we're going to make a new neural network that takes as input a point and a direction, and we're going to ask it, if I were to shoot a ray from this point out into infinity, what is the total transmittance that I would expect to see? Like, how much of that light will be visible along that entire ray? And if you have a neural network that does this, that can answer those questions, it's actually very easy now to do direct illumination, because you just, for each of these points, you just, instead of shooting a ray to the light, you just query a neural network once with the direction pointing to the light, and it returns a number like 0.7. And you say, great, thank you. And you multiply 0.7 into the color of the light, and you're done. The trick is, how do you supervise these models? And there's another trick for making that work, which is, while we're shooting rays from the camera, we actually get this total aggregate transmittance as a supervisory signal just kind of by accident. Like, in the process of doing alpha compositing along a ray, we will end up computing this for at least one direction along the ray. So we just have this signal sitting around, and we just train a network to supervise on it. And at the end of training, both the NERF and this other neural network are kind of in agreement with each other. And then you go on from direct illumination to indirect illumination. This is obviously, even more painful, because light will bounce off of stuff in the scene and then bounce off of the thing you're directly observing and then go towards the camera. So this is if direct illumination was intractable, this is unimaginably intractable. This is the age of the universe type stuff. So the trick here is that we train another neural network. So we've got 3 now. This third neural network is going to take in a point in space and a direction, and it's going to predict, if I were to shoot a ray in this direction, on average, where would I end up? Like, which is basically, where do you think the surface is in this direction? And if you have a network that can answer that question, then you don't need to trace rays to see where you'll bounce off of. If you're okay with this approximation that you're just going to bounce off of one thing, you can just jump straight to where the surface is and then query the first additional neural network that we were discussing, this transmittance one, to ask about the lights, and then you're done. Now you have indirect illumination, and it's expensive. You're asking a lot from these neural networks. You have to query them repeatedly, but you have to query them a handful of times for each point instead of a million or a billion. And again, we can supervise these things because when shooting camera rays, we get this supervision for free. We already kind of know these expected termination depths. We compute them by accident. And this works. We can use this system to take in a bunch of images of objects lit under different conditions and kind of do full inverse rendering. We get surface normals, albedo. We can ask about the direct and indirect illumination as separate things. And you can do all the things you'd expect to see with this. And the results are not perfect. There's a kind of characteristic bumpiness, which is probably because we're not regularizing this at all. And I definitely don't consider this to be the final word on neural inverse rendering or anything. But it's I think these ideas of using these auxiliary neural networks to kind of get extra information from and ask extra questions from, I think is a general purpose good idea. We got lots of nice visualizations where we're moving a point around on a surface, and we're asking the neural network to tell us things like the visibility environment map and predicted reflectance in different directions. It takes a little time to get used to kind of reading these visualizations. Maybe for some of the audience, this immediately clicks. There's a lot of content on the website. And again, the results are not perfect. So NERV is on the right there. It's really bumpy, but compared to solutions where you try to avoid reasoning about the geometry of the scene, which is what we have on the left, we're just asking the neural network to learn all of lighting from scratch. And it does an okay job, but it's like, obviously, it doesn't look like reality, right? The shadows being cast don't look like shadows. It's a very bad neural approximation to a physical process. And because NERV is constrained by the physics of ray tracing and geometry and materials and things, the renderings, as imperfect as they might be, they do look like renderings of a physical thing. And I think this is consistent with the story of NERV, which is that there's a lot of value in having physics determine how image formation works, even if you're going to be using neural networks kind of powering the system underneath it. And we have some results where we can do relighting and we can do change the materials of things. We were very amused by the idea of these golden hot dogs. And that's all I've got. Thanks so much for your attention. And I left a lot of time for Q&A. I'm hoping we can have a nice discussion about this stuff.
Thanks a lot. There's already lots of questions that have been asked during the talk. And there's this nice feature where anybody can vote for questions which give us a priority list. So I suggest that we just go through them, and I encourage the audience to actually come and ask the question by video. So if Merlin, Nimi, David wants to ask the question directly, otherwise I will just repeat it. Not sure it's working, so I will go straight. I think the question, many of us are overwhelmed by the number of follow-up papers. So instead of reading all of them, we will ask you what is the best paper we should look at. So what are the most interesting papers you've seen since the NERV and that we should look at?
Yeah, I'm struggling to think of a good answer. At this point, I agree. This is overwhelming. This is a really hard field to follow. The paper that I was most struck by is this paper called KiloNERV, which basically instead of having a single monolithic neural network that describes the entire scene, it just cuts the scene up into chunks. This is this is a huge win in terms of performance. They were able to get like 1000x speedups. And it's mostly on like, I mean, most of the challenge here is kind of like the performance engineering side of it. This is a thing that I find very interesting or very important because speed is a really limiting factor for doing a lot of the work in this space. And no one has really seemed to beat NERF in terms of quality, but there are lots of other techniques out there that are much, much faster. And I think that the thing that really kind of wins the day is going to be something that is in between these two things. I think there's a lot of interesting systems challenges in getting that to work. And yeah, I don't know. I mean, what the papers that I find interesting, I don't know. I think all the papers in this inverse rendering line are really important and good and worth thinking about. Nerves is one. There's another paper called Nerd. And there's several papers that are kind of coming out of the sort of the SDF side of this that are also doing similar things. And I find those all to be very compelling and very interesting.
So actually the inverse rendering is related to the second question in the list by Animesh Karnewar. Animesh, do you want to ask the question directly? I'm not sure this feature is working. So you already showed in the end of your talk the ability to recover shape, material, and lighting separately. That was related to his question. How much can you offer in terms of controllability? So do you want to expand or what you showed is on what you showed?
Sure. So in Nerve, everything was pretty. So in Nerve, and in other papers like Nerd, the goal is kind of interoperability with normal graphics engines and controllability from like as though you're in Blender or whatever, where point light sources are point light sources, you can change them, and materials are just normal microfacet material models that you could swap in, so that seems to be that seems to be fine. It seems like that is doable. There are other works that kind of have like neural rendering systems, like neural materials and maybe neural approximations to light. And these are also really promising. That usually you sacrifice controllability for quality because you have this magical neural black box that can do some cool stuff that you couldn't do if you had an analytical formulation, but then you lose controllability. And I don't know what the right breakdown is. We're trying to make these models kind of interoperable with normal graphics engines because we think that's going to be a very impactful way for these things to affect the world. But also, I mean, it is reasonable to think that we might want like neural standards for materials, or like it's not that crazy to have these things be fully neural, to have fully neural material models. Although I don't, that isn't to say that I think we should get rid of normal classic graphics engines. As for dynamic scenes, there is a lot of work on dynamic scenes. I didn't have enough time to talk about it, but we have this paper about deformable neural radiance fields. There's a paper called dynamic neural radiance fields. There's neural scene flow fields. I think I'm saying that wrong. There's a lot of papers about like NERF plus motion. It was a thing that people investigated very heavily in like the 6 months after NERF came out. That seems to work. It's not, I mean, there's a lot of problem with like rigging and stuff. Like I haven't seen very many results where people rig a dynamic NERF, but I haven't seen anything in which things are simultaneously dynamic and inverse rendering. That seems challenging. That's just going to be like a hard battle, but it seems doable.
Okay, thank you. Michael Fischer had a question on Fourier features, I guess. Michael, do you want to state it?
Can you hear me?
Yep.
Yes, thanks.
Okay, perfect. Hey, John, thanks for the great talk. So recently I was playing around with both like positional encoding and the Fourier features. And in my experiments, performance-wise, like considering the visual fidelity, they were kind of in the same ballpark. So I went back and looked at your paper, and I think you have some figures in there comparing positional encoding to the Fourier features, which also look quite similar. So do you have anything to share on which one's better or worse?
Yeah, in the paper, in that NERF's paper, we saw an improvement from Fourier features, but only using like simplified versions of NERF. And then in the more complicated versions of NERF, it was like there was too many the interactions between all the components made it hard to determine what was a good idea and what wasn't. There's also this other weird problem, which is that positional encoding uses axis-aligned sinusoids, and in these synthetic data sets that we were using, usually the objects are presented axis-aligned, like where X and Y like line up perfectly with right edges, like with corners in the object. And positional encoding is better in those cases, and it only stops being the case if you rotate things. I think in practice, positional encoding has been sufficient for all of our purposes and seems to be a good go-to solution. And the Fourier feature paper, I think, should be viewed more as like a theoretical analysis. Like the random Fourier features were like what let us do the analysis we were doing, and they explain away positional encoding to some degree. I don't think that either of them is the right solution forever, but I would say positional encoding it's just so easy to implement and to think about, and you can get like a hard band limited thing. Like you can just know where the cutoff is and where it wraps around. So that's what we all use, and that's what I would recommend. This space is still something of a mystery to us. Like we see a lot of contradictory results, and we don't know how to interpret. So I share your confusion and your dissatisfaction.
Okay, perfect. Thanks.
That's reassuring in a sense. Next question in the list is from Jan Novak. Yeah, Jan, you're online.
Yeah, I have a question regarding the two paradigms that you mentioned, Paradigm 1 and Paradigm A. As a rendering person, I'm freaking out thinking that Paradigm 1, which is neural network is producing the final pixel colors, is going to be the approach in 10 years, the more prevalent approach. I'm freaking out. It's actually about job security, kind of, right?
Yeah.
If neural network replaces all the algorithms that we have been inventing at EGSR and other conferences in the past, I don't know how many, 40 years, that's scary. So with all the stuff that you see around you at Google and at other companies and universities, what's your bet on in like the 10-year scale? You know, like is it going to be neural network producing the final pixels, or is the neural network going to be confined to something perhaps smaller within the scene? Yeah.
Yeah, I do think that the paradigm 1 of everything being neural, I don't think that's the way forward. I think that because if you take that approach, you then have you have this new problem of training a neural network to relearn all of physics from data, which is just like a bad way of doing physics. Like you shouldn't do that. Like it's going to be better to just write down, like have an array that you trace. That's always going to be faster and more accurate than having a neural network learn to do that, because at best it can reproduce it, but it's probably not going to reproduce it perfectly. And if it does reproduce it perfectly, it's going to be slower. That being said, I mean, a lot of this is about kind of what people is kind of the sociological side of this, right? Because especially Google, people at Google are very excited about building hardware accelerators for neural networks. And if you put enough resources into hardware accelerators for neural networks or software packages that make neural networks easy to use, then there's going to be people who just start using them for all sorts of things. And like I'm reminded of kind of like the rise, the trajectory of graphics, the graphics community. I mean, I'm something of a noob, but I get the sense that like a lot of the reason why kind of raster-based graphics took off at the beginning of like in the 90s is that like hardware made that viable and made that faster. So then people started kind of backing that more and more. So I wouldn't be surprised if pure neural rendering gets some traction just by virtue of there being ways to like a lot of energy and resources being spent on making it fast. But I do think at the end of the day, people are going to do the thing that works best, regardless of what, at Google, certain things are fast because we have ridiculous like tensor processing units and stuff like that. That's not like a physical thing. That's just like a circumstance thing. And if you care about like watts and dollars and things, you'll probably want to do the thing that's the most efficient, which will be a hybrid model where you have lots and lots of graphics and geometry.
Thank you.
Thanks. Then we have a question from Juan Raul Padron Grife. So I will just phrase it. Do you think it will be possible to combine NERF and its extension in a single model for geometry, material dynamics, etc.? I guess it.
I guess I kind of touched on this. I do think it's possible. Yeah, it's going to be hard. I mean, a lot of these things are hard, just very slow to train. That's kind of like the limiting factor for a lot of these things. But I don't see any reason why that can't be done.
So actually, I will jump in. You mentioned faster method to render, but training is also a big bottleneck. So
oh, that's what I mean by slow. Yeah, the speed of training is a huge bottleneck. It's one that at Google we're able to work around this because we just have like big computers. But this is definitely a limiting factor for a lot of things. I think that we can make this faster algorithmically. I think there's lots of opportunities for speed ups there. But yeah, I mean, just the more complicated you make these things, the slower they are to render, no matter how smart you are about setting it up. So.
Mm-hmm. Thanks. So the next question is related to NERV. What are the cases where it will not scale?
Yeah, I mean, it still assumes there's an object sitting on a table and that the lights are all infinitely far away. And all the ideas that I was proposing, or the things we used for that, will just completely fail if you start having things in the world that emit light that are like a recessed lighting in your ceiling or something. Like a Cornell box won't work. I guess maybe it might work, but NERV is pretty polished. NERV works. Like you can use NERV to solve problems. The NERV, all this inverse rendering stuff, like there's years to go on this. This is going to be like a long, hard problem to get really good solutions to, especially if you want them to be fast.
Actually, just to be sure I understood, in your diagram you had just 3 lights, but you consider all directions. So you
oh yeah, in practice we have environment maps and stuff.
Okay.
Yeah.
All right, so there's still a few questions. If like Simon Fay, if you want to ask your question live.
Sure. It was just an observation, actually. I don't know whether you're familiar with the Perlin paper from about 1984 and 1986 for 3D solid texturing.
Mm-hmm.
You build textures out of functions. But he had an interesting observation that if you're building something like turbulence, which is built of a low frequency plus one at double the frequency plus again, that if you knew your footprint of the object, you could basically trim off those higher frequencies to avoid aliasing. And it just struck me it was very, very similar to what you were doing there. It was just merely an observation. Might be just interesting thing to
sure.
relate.
Yeah, I don't know about this free turbulence stuff, but I'm getting feedback from your mic. No, I'm mute. When we were starting with this positional encoding for feature stuff, we started with Perlin noise. Like we started by thinking like, all right, we need something that's like kind of a pyramid, and we need to have frequencies at different levels, and we need to compose them together to make the optimization work. And then we ended up where we were because it was the simplest and most effective thing that kind of was adjacent to that. I do think there's a lot of connections. Nothing is new, right? Like all of these ideas have been explored in some way in the 80s and 90s in a graphics or image processing context. And I think that like our role here is to modernize them with machine learning, which sometimes is straightforward. Sometimes it means implementing it in TensorFlow. Sometimes it means like you really go back to basics and rederive things from scratch, and it's a mixed bag. But thanks for the pointer. I'll check out that one paper. I haven't heard of that particular Perlin paper. I just know the other ones.
So we will have to conclude because the next session starts at 6:10. There's maybe this very last question by Abhijit, if you can ask it concisely, and John, if you can answer concisely as well. Or John, if you can read it directly. And Abhijit.
Hi, John. Great talk. I was just wondering how is this training done? From, let's say you have a multi-view data stream. Just doing structure from motion, you'll get noisy depth estimates. So how does the neural network train to get such fine scale understanding of each voxel, and is it just that kind of noise gets smoothed out during the training process? How does it?
Sure. Well, so we use SFM for real images, but we only use the camera pose. We don't use any depths or anything. But the inaccuracies in the camera pose is definitely a huge problem, and they are always a little wrong. And that does show up, and it shows up as basically blur. Like if you haven't modeled the camera distortion and the fringes very well, you will get blur in the corners of the images, which is a pretty good failure mode. But ideally, we would not do that. There's some work that tries to solve for the camera poses.
But the results you showed, like they have fine scale features like petals of flowers in front of bushes, or like metal rods and with gaps. that would require super precise
yeah,
right?
But I mean, so we use call map for everything, and like it works. These packages are pretty mature, so they're able to do a decent job. It's camera intrinsics, like distortion-y type stuff is where they seem to be limited. But yeah, I mean, ideally, I mean, we would like Nerf to just be the photogrammetry package. You just give it images and it just does everything from scratch. I don't know what it would look like for that to do that, but a unified system where you can. You can solve for poses and the world simultaneously would be great. And there's some work on that. There's a paper called Nerf --, and another paper called BARF you can check out that that do this. And they don't show better results than using structure from motion packages, but they show that this idea kind of works, and I think it'll eventually work.
Great, thanks a lot.
Thanks. We will end with this grand challenge, and we'll thank you again for this very insightful talk.
Thanks, everyone. This was really fun.
And we'll be back in 5 minutes. Thank you.
Test. Hi, everyone, and welcome to the image and video editing session. This is our third and final session for today, and we're going to see 3 very exciting papers, so let's get started. The first paper we're going to see is called Video-Based Rendering of Dynamic Stationary Environments from Unsynchronized Inputs. And it's written by Theo Tonat, Yagis Aksoy, Mika Aitala, Sylvain Paris, Fredo Durant, and George Gretakis. And Theo is currently a postdoctoral researcher at Adobe Research Paris, where he works on real-time rendering and interactive path tracing. and he completed his PhD at INRIA Sophia Antipolis under the supervision of George Gretakis, where he focused on multi-view image processing. So let's get started with the talk.
Hi, I'm Teotona. In this talk, I'm going to present video-based rendering of dynamic stationary environments from unsynchronized inputs. This work was a joint effort with Yagi Zaksoy, Mika Aitala, Sylvain Paris, Fredo Durand, and George Gretakis, and it was a collaboration between INRIA, Adobe, MIT, and ETH Zurich. Image-based rendering is a powerful tool to render realistic scenes, providing viewpoint navigation using only casual capture consisting of photographs. However, when applied to scenes with dynamic content, it fails to capture the liveliness as would a simple capture video do. So in this work, we're looking into how to extend traditional IBR techniques to videos. Our casual capture setup, similarly as traditional IBR, will be just a few photographs and a simple capture setup with one smartphone with a tripod. But it also makes our capture setup unsynchronized. We also would like to enable viewport navigation as would traditional IBR do. In order to meet those requirements, we limit ourselves to stochastic elements such as water, fire, or waterfall. This type of scene poses many challenges due to the dynamic elements and the unsynchronized input. It is basically a nightmare for multi-use theory construction, so it provides little or no dynamic geometry. There are transparency in the scenes. The unsynchronized content makes blending very difficult, and the presence of temporal discontinuity and also problems due to screen space image stitching are very difficult and arise during compositing. There are many work focused on video-based rendering and image-based rendering, but regarding video, there are, for example, all the work about exploring video datasets are more focused on transition between different video and make the transition as appealing as possible, rather than enabling viewpoint navigation. The method related to cinema graphs enable to capture the dynamic effect by making or by producing short looping videos. However, they only deal with one video, making any spatial exploration impossible. On the other hand, producing accurate video reconstruction of difficult field animation, such as with tomography, requires a very constrained capture setup with a lot of synchronized sensor and high frame rates. IBR techniques enable viewport navigation for static scenes by weighting the contribution of each input view using either crafted formula in the case of unstructured dummy graph, or by learning the weights, for example, using the work of deep blending, or by using a volumetric consensus to drive the blending in soft 3D. More recent work with neural radiance field, which are the state of the art regarding quality of image-based rendering techniques, are restricted to scenes which are coherent, so they do not deal with unsynchronized content. So in our work, we start from a set of images and a set of videos, unsynchronized videos from a scene. And after a set of preprocess, where we both provide an approximate geometry in 3D and a per video segmentation of the dynamic elements to ultimate transparency, it enables at runtime to rely on a novel spatio-temporal video compositing method to provide real-time and viewpoint rendering of the scenes. So focusing first on the spatio-temporal video compositing part. In this part, we assume that we have already access to an approximate geometry and that matching, if necessary, is available. And the remaining issues are the unsynchronized content and the temporal discontinuity. And remembering that standard IBR techniques deal with the screen space image stitching issues by using blending field, we seek a video representation and a blending method that is able to solve the unsynchronized issue and the discontinuities while still being compatible with standard image-based rendering techniques. So looking at two synchronized input videos here on the right, we can see that there are some coherency between the low temporal frequency. That is, the fire is not moving everywhere across the room. On the other hand, if we look at the high temporal frequency, we can see that they are highly video specific and very stochastic. So the key ideas of our method for blending is to extract those input temporal frequency and apply different strategy for each of those frequency, that is, applying a per frequency blending field. So in order to extract those frequency, we rely on a temporal Laplacian pyramid that decomposes an input video into a sum of different temporal frequency bands, which is different videos. So for example here, the high frequency represents the waves, the medium frequency represents the overall elevation of the sea due to the waves, and the temporal residual contains the average color information. So now, to apply this equation to the blending, we start, for example, here with two videos and their decomposition into three different frequency bands. Then we apply for each frequency a different blending field, that is, a very sharp blending field for the high frequency and a very smooth blending field for the low frequencies that correspond to what we will do with the standard IBR techniques. Then, after applying those techniques, those blending independently per frequency, we collapse the resulting pyramid and get our final result. This decomposition can also be used to perform a cheap video looping using a per pixel processing, which reduces the temporal discontinuity when playing the video back to back. But remember that we assume that we have somehow access to an approximate 3D localization to reproduce the textures. But in many cases, this is not possible because due to the poor multiview stereo reconstruction due to the unsynchronized inputs, we have to create it ourselves. For that, we use a hull-based approach in region in space where videos are consistent, and then we propagate the depth information to each video specific content. Our tool for that is to compute the total variation of each input video and extract a binary mass by thresholding the total variation. From those masks, we extract voxel occupancy grid from the segmentation that you can see here in green, and then by reprojecting this volume into each input view, we can extract a median depth map of this volume. But remember that these depth maps only provide depths in region where all videos are somehow coherent. So in order to provide an approximate depth to most of the dynamic content, we use an least square based optimization to propagate the depths guided by the total variation. So you can see here in the middle the median depth obtained from the voxel grid, and on the right the propagation, the depth after the propagation steps. We need also to provide a matching for scenes that have semi-transparent elements. I won't give details in this talk, but after this step we extract a background and a semi-transparent foreground video for each input views. So now that we have all those elements, the rendering algorithm is pretty simple. We first run a classic IBR techniques using the background videos reprojected using the multiview stereo geometry. It is still important to do that because there are still subtle dynamic elements in the background happening. For example, here, the variation of the light due to the fire. Then we render the foreground using our video blending techniques, that is, per frequency reprojection and blending, then a collapse. And finally, we perform a simple background-foreground compositing to get the final results. So here are some results and comparison. We compare with standard unstructured Lie graph by updating the texture at each frame, and you can see that we are better at preserve the high frequency details. Here we compare with Soft 3D, where we use the median video frame to compute the consensus volumes and then update the texture at each frames. Again, we are way better to conserve all the details of the input videos. Here, we are in an interpolation between two viewpoint setup, and we compare with the learning-based approach, which does frame interpolation. In this example, we can see that we prevent too much blending between the input views and retains most of the dynamic element present in the input videos. In this example, we see that we provide a plausible parallax for the waterfall, thus reducing considerably the distortion due to the wrong geometry estimation. We also are able to render a see-through effect such as this C here, where we reproject different frequencies at different depths. So here, for example, we reproject the residual on the sea bottom and the high frequency on the water plane, which makes a correct parallax for the waves. And this is particularly visible when stopping time and moving the viewpoints. In conclusion, we propose the first method that allows free viewpoint navigation for unsynchronized video of stochastic phenomena by using the temporal Laplacian decomposition as a tool for both video blending and video looping. And that with an appropriate preprocess, we can handle stochastic phenomena that are opaque, semi-transparent, or completely see-through. Thank you for your attention, and I'm now open to questions.
Thank you very much. A very exciting talk. Yeah, I think there you are. Hi. I think the idea of applying temporal Laplacian pyramids for blending and looping unsynchronized video. It's a very elegant idea. So we don't have any questions yet. Feel free to ask your questions. You can either enter them in the text box on the bottom left, or you can click on the top left and ask your questions via video. Please don't be shy. Maybe in the meantime, so when you're blending the dynamic content of the unsynchronized videos using your temporal Laplacian pyramids, the pyramids themselves, they are still unsynchronized, right? So the starting frame of each pyramid is just more or less random. So I wonder whether this representation would also be suitable for optimizing for an optimal starting frame for each neighboring view.
Yeah, that's a good question. But I mean, you can imagine, because I was still at this hypothesis that it's stationary, so like you actually don't need to have this kind of synchronization, right? That's you have this low frequency, which is mostly coherent, and this high frequency, which is stochastic, so you can just stitch the high frequency together. So we actually don't need to rely on that. But you can imagine, of course, that like there is this approach with like Cinemagraph where you could actually optimize for like loops of different lengths to favorize transition. So that's the way this is usually done in single video looping, is that you are actually looping for like per region loops or per pixel loops. And that's how you optimize for that. And in our context, you could imagine that, yes, like for a given input view, you want to look at the nearest neighboring view and optimize for the best transition at the best time. Yeah, it's of course like one possible direction of future work. But like the nice thing which we have in our concept is that it's basically like a per pixel processing, so you don't need to have this kind of information of this kind of pre-optimization. So yeah, it's more efficient to do like the way we did it. But of course, for better transition, like for example, you can imagine that in this case, like for actually, because of course it's not completely, for example, the fire is not completely stationary, so you can still track some shapes of the frames. And of course, you could imagine that having such kind of somehow tracking like what would be the best time to switch to from one viewpoint to another would be interesting. But of course, in a few viewpoint navigation setup where you actually don't control at which time you will move the viewpoints, I guess makes this kind of definition quite challenging.
That makes sense. So we have a comment and a question by James Tomkin. Says, nice work, this is a hard problem. Were there any considerations at capture time that might be tricky for a novice, e.g. scene selection with respect to the dynamic elements?
There is also like this requirement for sparsity, because of course, if you want to capture as many view angle as possible, you want your video to be, you want your video to cover as many angle as possible. But I would say it's like the same requirement as you would have today for standard photo capture. Like this, like I guess the only difference is that maybe. At least for our work, we rely on way more videos than we used images. So I guess you will need to be maybe a little bit more careful about the angular separation between the view, but that's the main difference, I guess.
Gurpreet Singh asks and says, nice talk. Did you try using your VBR approach to perform time-space interpolations for images like the X-Fields paper from last SIGGRAPH Asia?
No, we actually didn't try that. To be completely honest, we actually begin this work like a few years ago during my PhD. So we actually didn't try to implement like the latest field approach or nerf approach to compare it to that. But I'm not sure how it would perform and what will like the requirements with respect to unsynchronization. I would imagine that you actually need some preprocess to make somehow the content per coherent to be able to have those, to enabling such coherent blending at runtime.
Great. So I think we've run out of time for questions. So please give another round of applause for Theo for a great talk. And
thank you, Julian.
Thank you. And we will move on to the next paper, which is called PosterChild, Blend-Aware Artistic Posterization. And it's written by Cheng-Keng Chao, Karan Singh, and Yotam Jingold. And Cheng-Keng is currently a first-year PhD student at George Mason University, where he's a member at the Creativity and Graphics Lab, led by Yotam Jingold. And his research interests lie on the intersection of arts and computer science, and his work aims to help artists to facilitate image editing tasks. So let's start the talk.
Hello, I'm going to tell you a project called PosterChild, Blend-Aware Artistic Posterization. This work is done by me, Cheng-Keng Chao, my advisor Yotam Jingold, and also our collaborators, Professor Karan Singh from University of Toronto. So before going deep into our approach, let me give you a small introduction on what exactly is artistic posterization. So posterization is an artifact in which an image with continuous color regions converted into an image consisting of smooth, constant color regions. So these are manually created by artists, and artists would like to exaggerate or recolor regions in their posters. So here's a small example of a teaser poster from EGSR website, and these are the results created by our algorithms. So you can see that our algorithms preserve the colors and have constant color regions, and also has smooth color boundaries. So people haven't directly dealing with this problem before, but there are some related previous work. So let's go into our problem statement. So our goal is to create a posterized image by using just a set of colors and also facilitate artists on recoloring. So automatic posterization tools like Photoshop or Illustrators, they actually create some artifacts such as like noise, color boundaries, or color saturation of small layers are given. So artists tend to create posterization effect by their own workflow. So if you try to Google like posterization, you will be able to see many kinds of tutorials. And for most of the tutorials, artists are tired of tracing enormous number of boundaries and applying different filtering technique and different color boundaries. So this is a really extremely tedious process. So if artists want to transfer this kind of posterization style into other image, they need to do it again. So this is one of the examples. This is created by Photoshop's automatic posterization filter, and this is artist creation. So you can see the frog in the middle. The Photoshop does not even posterize the frog, and the background is having noisy color boundaries, while artist creation is perfect. So our approach, our algorithm is based on principal steps carefully designed to capture artistic design requirements. So it breaks up into 4 steps. So first step, we probably would choose a color palette. And how do we actually choose it given input image? We use a convex hull-based palette extraction to get a palette. So the second step will be forming a approximate solid color regions. In this step, what we are doing is we assign the colors and to find rough regions. So given an input image like this, after step 2, it should be something like this. So it means that we convert the continuous color regions into a constant color regions, especially for head, as you can see. So the third part will be improving the region color blends. In this step, after getting the result from the second step, we have constant color regions. So for each region, we will perform local blends refinement to make the color matching better at that region compared to the color in the original image. So the final step, as you can see from here, and here, and here, after blend refinement, when I click, there's a slight color differences here. So after the final step, after the third step we perform on the final step will be improving the region boundaries. You can notice that after the third step, these boundaries are not smooth. So how do we actually smooth it? We utilize a high-pass filter to smooth the low frequency area like this. So at the same time, we smooth out the boundaries and also preserve the details. So that's going to the first step, convex hull-based palette extraction. So basically our goal, a really important property of algorithm is that it creates like constant color regions and involves gradation of tones in continuous regions such as like skin, sky, or sunset. So this motivates us to think about finding represented colors and blending those colors together to achieve gradation of tones. So we actually utilize Tain et al. 2016 method, and we perform a slight improvement on that. We use a k-means clustering to remove outliers on the input because convex hull-based algorithm is sensitive to outliers. So for more detail, please refer to our paper. So here's one of the examples showing what exactly the gradation of tone is. You can see like on the sky, in the sky, there's like continuous color regions, but after palette extraction and our algorithm pipeline, the final poster will be having constant color regions on the sky. So the second step will be rough region color assignment. So if you look at the posterized image, like example in the previous slide, like you can see like colors are being placed in different color constant regions. So our goal actually is partition image into color regions. And at the same time, the color in that region does not deviate too much from the original image. And at the same time, has spatial coherence, spatial consistency. So we can formulate this problem as optimization problem. And there are 2 terms in our optimization formulation. The first term is E data. So how E data is actually going to measure how differently the given color at the pixel P compared to the given input colors at pixel P. So if you sum it up, it will become along all the pixels in the image, it will become E data. So the second term here will be E pairwise. So E pairwise is at the pixel P, you compare to neighboring pixels Q, and then to see how color differences between P and Q. So we measure low energy inside RGB space and under L2 norm. So for different norms or different color spaces details, please refer to our paper. And so finally, our formulation will become kind of like this, like E data time plus lambda times E pairwise. So lambda here will be a clumpiness to control the clumpiness of the output poster. And actually, we solve this problem using multi-label optimization. The approach is proposed from Boykov and Kamagorov 2001. So this is one of the examples. The painting here, after palette extraction, we perform multi-label optimization on the image, and we end up having constant color regions instead of continuous color regions. So you can see from this, these are not smooth boundaries. So smooth boundaries are performed in step 3 instead of step 2. So we talk about multi-label optimization. How do we actually create labels? So our labels creation comes from 2 steps. The first step is exactly the palette itself, P, and the second side will be the pairwise blends from the palette colors P. So it's, for example, given a palette's PI and another palette's PJ, and given a user's specific parameters B, we can create like D kinds of blends, like D blends between palette I and palette J. And we perform D blends, we create D blends for each pair of palettes. So for example, given the Obama image here, after extracting the palettes, we have D0 here. D0 means that we only use palette colors. So as D grows up, we can see that there's like more and more constant color regions in Obama's forehead. So we eventually combine step 3 and step 4 into like region refinement. For step 3, we are going to perform a local blends refinement. So for each region, we formulate a quadratic Turing problem that minimizes the measurement between palette colors and the forbiddenness in the product. So for more detail, please refer to our paper. And by doing step 3, this can make us make each region like having better color matching compared to the original image. And for step 4, we smooth region boundaries. So the result from step 3 is not smooth. The region is not smooth. So we actually compute discrete Fourier transform and compute inverse discrete Fourier transform back to get a high pass filter. And we just perform median filter on low frequencies area. So you can see like a forehead, for example, the boundary being smooth. So the result of the algorithm can posterize anything like the architecture here, and we can easily like coloring in real time by just changing the colors in the palette, like here. And our algorithm can posterize the famous artwork, and we can just recolor the famous artwork by changing the color in the palette in real time. So final evaluation, our result compared to different approaches. We also compare to a direct k-means method. So as you can see, like small k is given, there will be color saturation. Even working on RGB XY space, there's like noisy boundaries here, while ours has smooth and constant color regions. And in this case, we are using just 44 colors. We actually did experimented using 44 colors for k-means, and you can see like almost no posterization effect on the image. So we perform a user's expert study with a professional artist with our GUI. So for more detail about study, please refer to our paper. So in conclusion, our PosterChild could perform like similar poster compared to those created by artists, but in a time-consuming way. So artists could need to create poster like in a few hours, but our algorithm can output posters in just like within 3 minutes. Also, we support like palette-based recoloring in real time, and we outperform state-of-the-art automatic posterization tools like the one in Photoshop or Illustrators. So some limitations, we do not support real-time posterization because of the slow performance of multi-label optimization. And for outlier removal, we use k-means. K-means is notably slow, so it does not scale linearly. So this is the drawback. And also, we do not recognize the semantic of the input image. So the code and GUI will be available in Creativity and Graphics tab. So thank you for your attention.
Thank you very much for an excellent talk. Very interesting. Thank you. So we don't have any questions yet. So please, again, either ask them via chat, or I've been told, post a queue into the chat room if you want to ask an in-person question, like Gurpreet.
Yeah, hi, nice talk. I was wondering while you were giving the talk, if you can use your posterization to improve the printing quality of the colored images, right? Because especially when you have very high quality images, you're prepared using some kind of high-end software. Printing is really a challenge because if you use like normal inkjet printers, they will show some bending artifacts even in the small flat regions. And have you given any thought like how this can be combined with your posterization idea?
Actually, we have bumped into some experiment on vectorize our posterized result, but it ends up with pretty difficult problems because it's not. Although we have segmented image, but it's actually not an easy problem to solve. So we end up not solving that because it's not our goal to generate a new algorithm for color vectorization. Yeah.
And if you stick to just digital mode, like not really the printing mode, do you foresee like how this can help in tone mapping, for example? Like there is, of course, you can use always dithering to compensate for many things, but maybe this could be something which can also be explored.
Yeah, exactly. And actually, we have in the future work in the paper, we describe something like in the future in the application we can do something like fatigue or generate some fatigue or by the algorithm because we have layers. So yeah.
Okay. Thank you. Yeah. Thanks a lot. Yeah. Very nice talk. Bye.
And I see Adrian wants to ask a live question as well.
Yes. Yeah, thanks for the talk and the nice illustrations. If I understood well, you first extract the palette, you fix it, and then you perform the segmentation, right? Did you consider iterating this process, like update the palette based on the segmentation?
That's a pretty good point. But in this case, we didn't consider that because multi-label optimization is pretty slow. So reassigning labels will cost us a lot of time. Yeah.
But do you think the update will make a difference? Like if you take the average color of a region, is it close to the color of the palette, or do you think there will be some changes?
I think it will be pretty much the same, like pretty similar. So I like my hunch is not really worth doing that. Yeah. Yeah.
Okay. Thank you.
Okay. So maybe one last very quick question. So more user-centric question. So the method you present is aimed to facilitate posterization, right? By automating certain steps. At the other end, it's an artistic tool, right? And the user wants to have like maximum control over the outcome of the algorithm. So I wondered whether you got any user feedback on whether there's aspects where users wanted to have more control or whether they wanted to have it like more automated. Any insight on this?
Yeah, actually, we performed an expert study. So for a lot of details, we mentioned that in the paper. But like I think the takeaway is like those professional artists really like our tools, but like they say that our tool is better than the one, like automatic one in Photoshop and Illustrators. but our tool is definitely slow. So actually, we come up with a different approach, like downsize algorithms, and we include that in the paper as well. So yeah, so if you are interested, feel free to look at the papers.
Thank you.
Yeah.
Okay, so we're out of time for questions. Thanks again to Cheng Kang. And yeah, let's continue with our last talk for the session. It's called Semantic-Aware Generative Approach for Image Inpainting. It's written by Deepankar Chanda and Nima Kademi Kalantari. And Deepankar recently finished his master's degree at the Department of Electrical Engineering at the Texas A&M, where he worked on applying machine learning to computational photography. So let's go with the talk.
Hi everyone, my name is Deepankar Chanda and I will present our work on semantic-aware image inpainting. Distortions in images may arise during the process of acquisition or due to deterioration, masking, or image editing. Image inpainting is the task of reconstructing missing regions in these distorted images. Its applications include restoration, object removal, novel view synthesis, and compression, among several others. To effectively complete a masked region, an inpainting approach should understand the scene context, recover the semantic regions occluded by the mask, and fill them in with plausible textures. Image inpainting is an actively and widely studied area. Modern techniques for image inpainting use a learning-based approach, where they extract image features from deep networks to learn context and locate plausible features to fill missing content. But these techniques simultaneously learn scene semantics and synthesize texture, and so are unable to properly recover structure corresponding to the masked objects. Thus, they produce inconsistent textures and shape. A few approaches try to address this issue by using edges to provide structural information. However, they do not provide semantic context and thus have texture and color artifacts. Broadly, our idea is to separate the task of semantic scene understanding and texture synthesis to make it easier for the system to learn the inpainting process. Specifically, we first estimate the semantic map in the masked regions, then provide this information to the inpainting network to effectively synthesize the appropriate textures. Some of the methods also explicitly use semantic information. Song et al. Proposed to guide the inpainting network using a semantic segmentation map. However, they failed to utilize this semantic information effectively. Liao et al. Also proposed to use the semantic information. However, their approach independently predicts the semantic map and image content at a given resolution. This may cause a mismatch between the semantic label and the image content at a given location. To summarize our contributions, we propose to effectively utilize the semantic information through a conditional semantic-aware feature modulation to generate high-quality inpainting results. We introduce a dual discriminator framework which uses image and semantic context to generate visually pleasing results. We demonstrate an extension of the technique to allow user interactivity. We now overview our system that addresses better texture generation and semantic coherency. From a given masked image, we first estimate a completed semantic map. This completed map is then fed to an image inpainting system, which fills the corresponding missing regions in the image to obtain the complete result. We first illustrate the image inpainting system. Note that here we assume the complete semantic map is available to us. Later, we explain its estimation. We use a generative adversarial network to reconstruct the missing portions of the image. The generator takes the masked image and the mask as input. It is composed of an encoder and a decoder. The encoder imputes missing values, while the decoder uses adaptive modulation to effectively utilize semantic information and reconstruct the image using the semantic map. The segmentation map is fed into the transformation CNN, which computes class representations across multiple resolutions. These are used to compute parameters gamma and beta, which are used in the decoder to condition the input image features. The generator then produces the output synthesized image. We now demonstrate the effect of incorporating the semantic information through feature modulation through this example. As you can see, naively concatenating the semantic map with the input exhibits discoloration and poor intrasemantic texture. In contrast, by incorporating the semantic map through feature modulation, we produce consistent zebra stripes. Here again is the naive approach versus ours. In order to enhance the quality of the final result, we train using two discriminators. The inpainted image and the mask is supplied to the input consistency discriminator, which forces the generator to produce results that blend with the input masked image. The generated image, along with the semantic map, is provided to the semantic consistency discriminator, which ensures that the generator can associate feature and texture from the image to the semantic labels. Our optimization objective includes the adversarial loss, a discriminator feature loss, a perceptual loss, and L1 loss to improve the quality of the inpainted result. We'll now see the impact of using the dual discriminator framework. The generator produces blurry texture if a single discriminator is used, where both the semantic map and the mask are concatenated to the input. If only the input consistency discriminator is used, while the generated content blends with the inpainted image, we see that the interior of the mask has texture and color artifacts. On the flip side, if only the semantic consistency discriminator is used, the texture is captured well throughout the entirety of the masked region, but we see the seams of the mask. Our complete result is able to resolve these issues. That completes the description of the image inpainting system. We now describe how to estimate the complete semantic map. First, we use a pre-trained off-the-shelf network to generate an incomplete semantic map for the masked image. We then use a GAN to reconstruct the missing semantic labels and generate a complete semantic map. We use an adversarial objective for optimization, and to reduce noise in the predicted labels, we incorporate the total variation loss. We train our system in a two-phase manner. In phase 1, the label inpainting network and the image inpainting network are trained independently. In phase 2, we fuse the models and jointly train them in order to enhance the quality of the results. That finishes the description of our approach. Now we'll see some results. First, we show a quantitative comparison of each component of our method. We include a comparison across 3 perceptual metrics. A lower FID and LPIP score is better, while for SSIM, a higher score is better. When either only the input consistency or semantic consistency discriminator are used, we see lower perceptual quality scores. The single discriminator takes as input the image, mask, and the semantic map. However, it too performs poorly. The naive generator has significantly worse perceptual metrics. As shown through the earlier visual comparison, our complete system significantly improves the results. We now compare our results against 4 other approaches. We compare against Adobe Photoshop's Content-Aware Fill, EdgeConnect by Nazeri et al., DFill v2 by Yu et al., and ProFill by Zeng et al. We first show a quantitative comparison against other methods. As can be seen from the table, our method performs well across all perceptual metrics. Next, we'll see some visual comparisons. First, we show an example of image restoration. For each competing approach, we show our results immediately after for better comparison. We also toggle between results to better highlight the differences. We show a comparison against Photoshop, which is unable to understand scene context. In comparison, here's ours. EdgeConnect has severe texture leakage. DeepFill V2 has color artifacts. Profil also has texture and color artifacts at the arm and head. Now, we show an example of object removal. We remove the fold. Like before, Photoshop cannot understand scene context and hence produces inconsistent results. Here is our approach. In contrast, it's able to fuse the legs of the horse with the torso. EdgeConnect has severe blurring. DeepFill V2 has severe texture artifacts. Profil does not properly connect the legs of the horse to the torso. Next, we show an example of user interaction. In this example, the user manually edits the estimated semantic map to obtain the desired results. Although our automatically generated results are reasonable, with additional user guidance where the user manually edits the semantic map, our method is able to improve the shape of the legs and the stripe patterns. In conclusion, we effectively incorporate semantic information through semantic-aware modulation. We generate high-quality results by training with dual discriminators, the input consistency discriminator and the semantic consistency discriminator. We demonstrate a practical user interaction method. Thank you. I will now take.
Thank you very much for a great talk and very impressive results. So let's wait a second for Deepankar to show up so we can ask him questions.
Hi there. Sorry about that, Julian.
Hey, Deepankar.
Technical difficulties.
We have a question by Gurpreet.
Yeah. Hi, Deepan. I have a quick question. So the last slide which you showed, I was wondering about that regions. For example, if there is a thin structure like zebra leg, and the region you have picked is quite bigger, so the background is kind of more dominant in this neighborhood. So how would the image in painting would behave? Like, how would it know that, okay, it has to take care of this anisotropic structure of the leg of the zebra and not really just fill it up with the background grass at that place?
That's where the semantic map comes in. One of the things that we noticed during the experimentation was that if the semantic structures are, if they're visible and if they're not extremely thin, for instance, if the semantic structure occupies a relatively larger width, then the network's able to use the information from the semantic reconstruction itself. And so it's able to, essentially it uses the edges that it predicts in the semantic map to join the disconnected regions in the semantic area, and then it's able to just inpaint that. But if the region that's to be inpainted, for instance, if it was just a pole, if that's very thin, then the inpainted semantics would simply be the background, and so it would be difficult for the method to reconstruct to join the two.
I see. But the semantics are learned by the data set itself, right? I mean, it's
yes.
I see. So if so there is nothing really guides other than the dataset. If the dataset does not capture the semantics properly, there is no way to make any correction there.
There is actually the total variation loss that we use is another thing that actually helps guide the process, because in a manner of speaking, if the masked region is not too large, and so long as the mask adequately, so long as the mask is not too large relative to the width of the object, the total variation loss essentially imposes connection between the two disjoint parts. So it's the dataset alongside the loss function that helps ensure the consistency in painting the semantic region.
I see. Okay, thank you.
Thank you very much. I think we have time for one more question. So if anybody has a question, this is your chance. So maybe I'll ask a question. So both for the adversarial framework and the semantic map estimation, you optimize a loss function containing like 4 or 5 different sub-losses, right? The adversarial loss and content loss, feature loss. So I wonder if you've ran any hyperparameter optimization on the weighting between these terms, or how did you determine the weight?
We did perform a random search for hyperparameters that are associated with the loss functions, and well, after the hyperparameter search, we certain that the ones that we have currently yield the best metrics in terms of the FID and the LPIP score, and it's on the basis of that we decided the values for lambdas.
Thanks a lot. Yeah, so I think we've run out of time for questions. Please give another round of applause for Deepankar for a great job and a great Q&A.
Thank you, Julian.
And I'll pass it to Pascal.
Hi, everybody. Thanks to all the speakers and all the chairs for yet another great day of EGSR. Now, next up is our social mixers. And today they're going to be even better than yesterday, so make sure to join. They will start in 3 minutes. And if you want to take part, then please head to the social hub on OYA. See you there.